In this video, I'm going to cover chapter 7 of my stochastic modeling book. That's the chapter about discrete time Markov chain, which is the most common, the most popular type of stochastic processes we typically find in practice. Here are more precisely the different topics we are going to cover. As usual, I represented that in the form of a connected graph to also underline the logical connections among the different topics. And as for the previous videos in this playlist, check out the description of the video where you can find the table of contents with the different topics and the corresponding timing. So you can just click on the timing to go to the part you are interested in. At the end of the description, you will also find a link to the presentation I wrote for this video. Just click on the link if you want to download the PDF file I'm going to use here. So the concept of Markov chain was introduced by Russian mathematician Andrei Markov. I mentioned him in chapter 4 of this playlist. I also added a picture of Andrei Kolmogorov that I mentioned in chapter 1 of this playlist. Is the father of modern probability theory. Is also one of the main contributors of the field of Markov chain. Right, so the three main questions about Markov chain are about the fraction of time spent in a state in the long run. That's the quantity that we see here and here, okay? A second important quantity we want to understand is what we call the mean recurrence time. It's defined as the expected number of time steps you need to return to a state. And a third main quantity we want to understand is this quantity here and here. These are called the limiting probabilities. That's the probability of finding your process in state Y in the long run as time goes to infinity, given that we start from state X. All right, so the three main ingredients that we need to answer those questions are the concept of irreducibility, okay? Then the complementary concept of transient null recurrence and positive recurrence. And then a third important ingredient that we need to have also convergence of those limiting probabilities is called aperiodicity. Okay? So the goal of this video is mostly to describe those three ingredients, see how they play a role in proving existence uniqueness of those different quantities at the bottom. Okay, and also another important quantity that we are going to see that is also important, that's the notion of stationary distribution. The stationary distribution of your process, if it exists, is going to give you the value of those different limits. All right, so that's kind of the global picture of this video. So more precisely, first I'm going to show that a discrete time Markov chain is fully characterized by what we call its transition probabilities. And having the transition probabilities, you can define what we call the transition matrix. You can also draw some directed graph, like I want to call that the directed graph associated to the Markov chain, that gives you some kind of visualization of the dynamical structure of the process. All right, so that's going to be the first aspect. Then after, we'll see how we can use the transition matrix to compute what we call the multi-step transition probabilities. That's the probability of going from a state to another state, not in 1 unit of time, like for the transition probabilities, but in n unit of time. N can be any positive integer. We'll see how, so I'm going to define this notion, and we are also going to see how we can compute those, at least in theory, using the transition matrix. All right, so next step, using those multi-state transition probabilities, we can also define the notion of communication classes, okay, which brings us to the notion of irreducibility. We said that a discrete time Markov chain is irreducible if it has only one communication class. I'm also going to show you how you can use the directed graph associated to the Markov chain rather than the transition matrix to find easily all the communication classes. All right, so then next step, we'll see again that those multi-step transition probabilities can be used to check whether a state is recurrent and transient. So I'm going to define those notions of recurrence and transience. We'll see that there are particular cases where it's easy to check that a state is recurrent or transient. In some situations, things are a little bit more difficult, and you need to look at those infinite sum of those multi-step transition probabilities to be able to check whether a state is recurrent or transient. Using this result, we'll also be able to prove a connection between recurrence, transience, and communication classes, in the sense that those two notions are what we call class properties. That means that all the states in the same communication class must all be transient or must all be recurrent. You cannot have a mixture of the two states, of the two different types of states. All right, so that's going to be the next step. Then after, we can move on to the very important concept of stationary distribution. Okay, the stationary distribution is more or less like an equilibrium, but for your discrete time Markov chain. And I'll show you how we can use the transition matrix to easily compute the stationary distribution when there is one. I'm going to give you other tricks to compute the stationary distribution using what we call doubly stochasticity when it's the case, or reversibility when it's the case. All right, so this is more or less like all those aspects are more or less like the kind of background we need to be able to answer those questions at the bottom. The second part of the video will be about answering those three questions. And so first, what I'm going to do is prove, so one of the main theorems in the field of discrete time Markov chain, which says that if you have an irreducible Markov chain, either all the states are transient, all the states are null recurrent, or all the states are positive recurrent. Null recurrence and positive recurrence also are class properties that do not change across the same communication class. All right, so we'll prove that. We'll also prove that in the case of transience and null recurrence, the fraction of time spent in any state goes to 0. At the opposite, if the process is positive recurrent, then there is a unique stationary distribution here that we'll call pi, and the fraction of time spent in state y in the long run is going to converge to the corresponding coordinate of the stationary distribution. So that's going to be the first main answer to the first main question. The fraction of time spent in a state converges either to 0 or to the corresponding coordinate of the stationary distribution when there is 1. Using all that, we can also easily answer the second question about the mean recurrence time. We'll see that the mean recurrence time at state y is just the reciprocal of the corresponding coordinate of the stationary distribution. Right, so the last step will be to study the limiting probabilities here. What is the probability of finding the process in state y in the long run if we start from state x? To answer this, we need one more ingredient, okay? Irreducibility and whether the process is transient, null recurrent, or positive recurrent is not enough. We need one more notion. We need the notion of aperiodicity. So next I will, to be able eventually to define the notion of aperiodicity, I'm going to define the notion of period of a state. All right? We'll see that the period of a state can be easily found using the directed graph corresponding the directed graph associated to your discrete time Markov chain. We'll also see that exactly like transience, null recurrence, and positive recurrence, the notion of period is a class property, which means again that all the states in the same communication class all have the same period. All right? So in particular, if the process is irreducible, meaning only one communication class, then all the states of your discrete time Markov chain must all have the same period. If the period is 1, then we say that the process is aperiodic. And in this case, though this limiting probability, okay, is going to also converge to the corresponding coordinate pi y of the stationary distribution. in the positive recurrent case, but in the transient case or null recurrent case, then you again have convergence here to 0. I'm also going to show you that if you are in the positive recurrent case, but the period is not equal to 1, then those limiting probabilities here in fact do not exist, basically they oscillate. So to begin with, let's look at those notions of transition probabilities, transition matrix, and directed graph associated to a discrete Markov chain. So first, I'm reminding you the definition of a discrete Markov chain. I already defined that in chapter 4, but because this video is all about this, I remind you the definition. We said that the process xn, so n is an integer representing the time, so that's discrete time. So the process xn is going to be a discrete time Markov chain with finite or countable state space S if the probability that xn plus 1 is in a set B given fn is equal to the probability of the same event given xn. So if you think of n as the present time, xn plus 1 in B is going to be a typical event in the future. So those two probability rates like the probability of something, a very generic event, very general event happening in the future. Given fn, that's the natural filtration of the process, so you can basically replace fn by xn, xn minus 1, xn minus 2, up to x0. Okay, so the conditional probability of something happening in the future given past and present, okay, is equal to the probability of the same event but given only the present. Right, so this means that's written here, the interpretation is the fact that the future of the process, okay, and a typical event in the future again is of this form, depends on the past, here fn, past and present, but only through the present xn. That's the definition. You can, like the best word that would describe the Markov property, like the characteristic of a Markov process would be the word memoryless. Okay, the process loses memory of what happened in the past. To understand the future, you only need to know the present. Okay, that's kind of the meaning of Markov chain. Another way to say this thing would be to say that given the present, past and future are independent. All right. So now notice that in the definition here, I took any possible set, subset B of S. Strictly speaking, so that this is an event and so that it's measurable, you need B to be a Borel set, but because we assume that the state space S is finite or countable, any possible subset of S is in fact Borel. Okay, that's why I'm taking any subset B of S. That's the same as saying any Borel subset of S. Any subset is a Borel set. Notice also that I impose this condition that S is finite or countable. That's not a big restriction. In fact, most of the discrete time Markov chain in practice assume that the state space is finite or countable. So if time is discrete, then the state space also is discrete. There are Markov chain with continuous state space or uncountable state space, but those ones typically evolve in continuous time, not in discrete time. So this is a restriction, but not a big restriction. Right. So now, how can we study this process? How can we characterize this process? Well, because S is finite or countable, and so B also is going to be finite or countable, it's enough, like basically some equivalent definition would be to rewrite those conditional probabilities, but looking at a specific trajectory of the process and taking B equal to a singleton, let's say singleton Y, and then that would become that the probability that xn plus 1 is equal to Y, given that from time 0 to time n, the process visited state let's say little x0, little x1 up to little xn, is just equal to the probability of going from little xn to state y. All right? So this means that the process is fully characterized by what I want to call the one-step transition probabilities, the probability of going from a state x to a state y in one time step. Okay? So those probabilities that are basically conditional probabilities are called the transition probabilities of the process. That's basically the collection of all the pxy equal to the probability of going from state x to state y from time n to time n plus 1. So that's the probability of going from state x to state y in one time step. Okay? Those conditional probabilities are defined for all x and y in the state space. Okay? And from the definition of Markov chain, from the fact that we have memoryless, indeed, this type of process is fully characterized by its transition probabilities. Notice here that I'm making one more assumption, which again is very typical in practice. If you look at the quantity here, this quantity depends on x, y, but also n. Okay, you have time n here. But the quantity on the left does not depend on n. That's a typical assumption we make typically, and that says basically that the process is time homogeneous. That means that the probability of going from state x to state y is always the same. This quantity is not going to change over time. Okay? So we have a discrete time Markov chain with finite and countable state space. Okay? And the process is time homogeneous, meaning that the transition probabilities are not going to change over time. All right. So in practice, when you have to study a Markov chain, typically the process is described by a text in English. The first thing you want to do is to turn this text into equation, like quantify this text, basically, by first finding all those transition probabilities. Okay, all those conditional probabilities here. All right, so that's step one. Then, once you have all those ones so that they really become useful and you can do something with them, you can do two things. You can use them to define a matrix that is going to be a square matrix when S is finite. When S is countable infinite, then that's going to be an infinite matrix called the transition matrix. Or you can use those transition probabilities to define a directed graph associated to the process that is going to give you some kind of visualization of the dynamical structure of the process. So I'm going to define that carefully. So first possible representation of your process is in the form of a transition matrix, and the transition matrix is basically a matrix that I'm going to call capital P. So capital P, I'm using the same letter as for the probability, but based on the context, that's going to be obvious whether we use the probability P or the transition matrix P. Okay, so that's going to be the matrix of all the pxy of all the transition probabilities for all x and y in S. So the way you construct this matrix is by choosing an ordering of the states. Okay. You use the same ordering for the rows of the matrix and the columns of the matrix, okay? And then your matrix is going to be the matrix that has coefficient xy on row x, column y of the matrix. You will see the number pxy, probability of going from state x to state y. That's how you build your matrix. This matrix, again, can be finite, in which case that's a square matrix, or it can be infinite, okay? That's the first representation. Second representation in the form of a directed graph. In this case, you have a bunch of points, okay, that corresponds to the different states in S of your process. That corresponds to the vertices of your graph, okay? And then you are going to draw an arrow from X to Y if and only if Pxy is strictly positive. Okay? So the graph is going to have an arrow from x to y if and only if the process can indeed jump from state x to state y in one time step. But you don't do anything, there is no arrow, if you cannot go from x to y in one time step. Okay? So these are two important representations of your process, a matrix form or a graph form. Both of them are useful to study different aspects of the process. Sometimes it's better to have the transition matrix, sometimes it's better to have the directed graph, and in general, to really fully understand the discrete time Markov chain, you kind of want both representations. Alright, so now, so that you see in an example how that works, let's assume that we have a discrete time Markov chain with only 4 states that I'm going to number 1, 2, 3, 4. So that corresponds to column y 2, 3, 4 and row 1, 2, 3, 4. You have a square matrix, and that's an example of transition matrix here. If you look at the first row, what this means, what those numbers means, is that if you are in state 1, and I'm saying state 1 because we are looking at the first row, then you are going to stay in state 1 at the next time step with probability 1/2, or you are going to jump to state 2 with probability 1/3, or you are going to jump to state 4 with probability 1/6. But you cannot jump from state 1 to state 3. That's the meaning of this row. Okay? So notice that 1/3 plus 1/2 plus 1/3 plus 1/6 is equal to 1. And if you check the other rows, you will have the same thing. So this matrix is such that the coefficients are non-negative. And if you look at the sum of all the coefficients on the same row, this sum is always equal to 1. This type of matrix is called a stochastic matrix. Okay? The fact that the transition matrix is indeed a stochastic matrix is obvious. It follows from the fact that, in fact, those 4 numbers here, they correspond to the 4 probabilities of a probability mass function. Okay? You are given that you are in state 1. You can do 4 different things: stay in state 1, or jump to state 2, or jump to state 3, or jump to state 4. And so that's why those basically numbers, they are probabilities attached to events that all together form a partition of omega, of your probability space omega. And so that's why they add up to 1. Okay? So again, if you have a transition matrix, then all those coefficients are non-negative because they are probabilities, and the sum of the coefficients on the same row should add up to 1. That's exactly a stochastic matrix. And so what we have, the result we have is that if you have a discrete time Markov chain, then this discrete time Markov chain is going to be characterized by a stochastic matrix. At the opposite, if you have a stochastic matrix, then there is a unique discrete time Markov chain associated to this matrix, that would correspond to the transition matrix of this Markov chain. So there is more or less a one-to-one correspondence between the set of square matrices that are stochastic matrices and the set of discrete time Markov chain. All right, so that's an example of transition matrix. Now, notice that once you have those probabilities, you can construct this matrix. You can also construct the directed graph. But if you have the directed graph, then you cannot go back to the matrix, okay? Because the directed graph only tells you about whether those pxy are strictly positive or equal to 0, okay? So the directed graph has less information than the transition matrix. And so if you have the transition matrix, you can get the directed graph, but if you have the directed graph, you cannot guess the transition matrix. All right, so now let's see how, using this transition matrix, we can indeed build this directed graph. Well, in this case, what you would do is, you see step 1, the vertex set should be S. So In this case, S is a set with 4 states, with 4 elements. So I'm just going to draw 4 points here that I number 1, 2, 3, 4. That's the 4 different states of the process. And then you just look at the coefficients here, and each time you see something strictly positive, you are going to draw an arrow connecting like the 2 states, the 2 corresponding states in your matrix. So in this case, you get, for instance, this directed graph. So for instance, let's look at the flow out of 1. Here, you see that from state 1, you can go to state 1, 2, 4, but not to state 3. And that's what you see here. From state 1, you can stay in state 1, you can go to state 2, or you can go to state 4, but you cannot go to state 3. There is no arrow going from 1 to 3. Same story for the second row. From state 2, you can go to state 3 and 4, but not the other 2. And then in your graph, from state 2, you have indeed an arrow going to state 3, an arrow going to state 4, but you don't have any arrow going from 2 to 1 or from 2 to 2. Okay? So once you have your matrix, you can build your graph. The graph has less information, but it gives you some kind of visualization of the dynamical structure of your process and is in fact more useful than the transition matrix to study some aspect of your process. All right? So even if you are losing some information, okay, because you can go from the matrix to the directed graph but not the other way around, still the directed graph gives you a visualization that the matrix does not give you that will be more useful to study a qualitative aspect of the process. So more precisely, we are going to see right now that the transition matrix is typically useful to study quantitative aspects of the process, and we are going to see how we can use it to find, at least in theory, the multi-step transition probabilities of the process and also to compute the stationary distribution. At the opposite, the directed graph is better to study qualitative aspect of the process, and in particular I'm going to show you how we can use this directed graph to easily find the communication classes of the process or also the period of the different communication classes. So now let's define the notion of multi-step transition probabilities and let's see how we can use the transition matrix that we've just defined to, at least in theory, compute those probabilities. So the definition of multi-step transition probabilities is here. In general, for any 2 states x and y and any non-negative integer n, p sub n xy is going to be the probability of going from state x to state y in n time steps. So the time increment is n. Notice that if you assume that n equals 1, that's exactly the probability of going from x to y in 1 time step, and we get exactly the definition of transition probabilities that we just defined in the previous slide. All right? So the goal of this slide is to show a connection between those multi-step transition probabilities and the transition matrix we just defined. So the idea to show this connection is going to use something called Chapman-Kolmogorov equation that tells you more or less how you can rewrite multi-step transition probabilities using other multi-step transition probabilities, but where the time increment is shorter. Okay? So that's a result due to Chapman and Kolmogorov called Chapman-Kolmogorov equations. This is a tool I'm going to use to study those transition probabilities, but that's also a tool I'm going to use a lot after in this video. So the idea is that, again, you can rewrite the multi-step transition probability where the time increment is n plus m using the n-step transition probabilities and m-step transition probabilities. So the result is like the proof is only 1 line, 2 lines, okay? And that's just based on a basic conditioning. The idea is just to say that to go from state X to state Y in n plus m time steps, if you condition on anything that can happen at time n, you can say that, well, this is the same as going from state X to state Z in the first n time steps, and then from state Z to state Y in the next m time steps, okay? And you sum over all the possible values of state Z, and then you get your result, okay? That's how you prove this. The reason this works is because those events here, all the events that xn equals z, okay, n is fixed but z can be all the possible states. So all those events, they form a partition of omega, okay, of your probability space in the background. And so conditioning on this partition, you just get that the probability of going from x to y in n plus m time steps. That's the probability of going from x to z in n time steps, and then going from z to y from time n to time n plus m, okay? Sum over z. Then, after, you notice that this conditional probability, by definition, is exactly the same as here, but for y equals z, so that gives you this Pnxz here. Then notice also that by assumption, our Markov chain is time homogeneous, and so this over conditional probability is in fact a quantity that does not depend on n. That's just the probability of going from z to y in m time steps. So this conditional probability is just equal to Pmzy, and we are done, okay? So notice that what we did here is we were able to express some multi-step transition probability where the time increment is n plus m using over multi-step transition probabilities, but where the time increment is less than that, okay? And so that's the key to proving proving some connection between those multi-step transition probabilities and the transition matrix. And so more precisely, we have the following theorem that says that the probability of going from state X to state Y in n time step is in fact exactly the same as the coefficient xy of the transition matrix P raised at the power n. So the transition matrix itself is the matrix with the transition probabilities in one time step. If you look at the nth power of this matrix, you get a new square matrix, a new stochastic matrix, and now the interpretation of those coefficients is going to be basically the probability of going from x to y, but in n time steps. So the multiplication of matrices in linear algebra basically takes care of all those possible conditioning, and you end up with the n time step transition probabilities. All right, so how do we prove this result? Well, we are going to prove the result by induction on n. Notice that the result for n equals 1 is obvious by definition. That's the definition of the transition matrix. Remember that the transition matrix P is defined as the matrix of the transition probabilities. If you take P at the power 1 here, you just get the matrix P. If you get little p sub 1 here, you get the one time step transition probabilities that are what we just call the transition probabilities. So the result is true for n equals 1 by definition, okay? So that's the base case in your induction. The result is obvious for n equals 1 by definition. I also notice here that it's also true for n equals 0. So why is that? Well, if you take n equals 0 here, you end up with probability that x0 equals y, given that x0 equals x. Obviously, this conditional probability is either equal to 0 or 1, depending on whether x and y are different or equal. And so eventually you end up with that the matrix of the P0xy should be the identity matrix. But indeed, any square matrix at the power 0 is, by convention, the identity matrix. So that's also true for n equals 0. All right, so that's the base case. Now, how can we prove that, conclude, that we have indeed this by induction? Well, we are, as usual, to prove a result by induction, we are going to assume that this is true for some n, and we want to prove that it's again true at the next step, n plus 1. All right, so, and the proof is just like that. Assume that this is true at step n, and we are going to study the multi-step transition probability, but where the time increment is n plus 1, we are going to just apply Chapman-Kolmogorov equations, but when m is equal to 1, okay? If you take m equals 1 here, you end up exactly with Pn plus 1 xy is equal by Chapman-Kolmogorov equation to the sum over z of the Pn xz here, that you recognize here, times P1 zy, which is just P zy, and that's it. Okay, so that's consequence of Chapman-Kolmogorov equation. Then, after, by using our assumption that the result is true for n, at rank n, you can just replace this n-step transition probability here by the coefficient xz of the matrix P raised at the power n. That's our assumption. Also, because by definition P is the matrix of the Pxy, you can replace this Pzy by capital Pzy, coefficient zy of the matrix P. Now, if you look carefully at this expression, you see that x and y are fixed. X corresponds to the row of the matrix Pn, y corresponds to the column of the matrix P. But z moves, okay? Z goes through the state space. So what you do here, exactly looking at this sum, is you look at the first term, the first coefficient on row x, row x of the matrix Pn, and you multiply by first coefficient on column y of the matrix. And then you add same, but for the second coefficient, and third coefficient, and so on. So what you are doing eventually is looking at the scalar product of row x of the matrix Pn and column y of the matrix P. That's exactly, again, scalar product of row x and column y. That's the way we multiply matrices in linear algebra. And so this sum is, in fact, okay, by results in linear algebra, that's by definition exactly the coefficient xy of the matrix Pn times P, but Pn times P is obviously equals to P at the power n plus 1. All right. So eventually we get that the probability of going from x to y in n plus 1 step is indeed equal to the coefficient xy of the matrix P raised at the power n plus 1. So that indeed shows the result by induction. Okay, so we have this result. So now, in practice, you can, in theory, compute those n-step transition probabilities by looking at the nth power of the matrix. Except that if the matrix is too big and n is too big, typically you cannot do it. You are facing a problem not with probability theory. Probability theory here is neat. It tells you that this is the nth power of a matrix. Okay, so everything is well defined. But in practice, computing the power, like all the possible powers of a large matrix is basically impossible. And so this result, and I conclude this slide with this note, this result is not very useful typically in practice. You can use it to basically compute those n-step transition probabilities if the state space is very small, only 2 or 3 states, or if n is small, equals 2 or 3 only. But again, if S is big and n is bigger than that, then you are lost. So this result in practice is typically not useful. But we are going to see that this is in fact a very important result in theory. Using this result in particular, we are going to be able to give some kind of very specific characterization of the stationary distribution of a discrete time Markov chain. So now using those multi-step transition probabilities, we can also define the notion of communication classes, which is very important in the field of Markov chain because it's related to the notion of irreducibility. I'm also going to show you how we can use the directed graph associated to the process to find those communication classes. So let's start with this definition. We said that two states x and y communicate, and I'm going to use a double arrow like that to show that they communicate, to indicate that they communicate. If we can find two finite integers, n and m, such that Pnxy is strictly positive and Pmyx is strictly positive. So basically what this means is that two states x and y communicate if and only if you can go from x to y and from y to x, both with positive probability in a finite number of steps. Alright, so notice that this defines a binary relationship on the set S, and a natural question about binary relationship is whether they are equivalence relationship or not. And that's our first result. We can prove that this is indeed an equivalence relationship on S. Before I prove this result, I want to give some consequences of this result and also a few more definitions. So, basic result in math tells you that if you have an equivalence relationship on a set, then this relationship is going to induce a partition of this set into something that we call equivalence classes, where all the elements in the same class are in a relationship, but elements in different classes are not in a relationship. Okay? So that's just a basic consequence of this lemma. This result induces a partition of the state space into equivalence classes that in this case we are going to call communication classes. So let's assume that we have a discrete time Markov chain. This square represents basically the state space S of the process, and let's assume that we have, in this case, three equivalence classes. Then a natural question here is it possible, for instance, to go from state X to state X prime in a finite number of steps, and to go then from X prime to X double prime in a finite number of steps? Okay? Those three states are in three different communication classes, so intuitively we might think it's not possible, but in fact the answer is yes, this is possible. This does not contradict the definition. So why is that? Well, that's because by definition, saying that X and X prime communicate, which would contradict the picture, would mean that we can go from X to X prime, but also we can go from X prime to X. And that's not what the picture says. The picture only says we can go from X to X prime. So have in mind that it's possible that two states, X and Y in general, are in different communication classes. Still, you can find N such that Pnxy is strictly positive. But then if it's the case, then this part is not true. You can no longer go from Y to X in a finite number of steps if X and Y are in two different communication classes. Okay? So, again, this picture, assuming that you have three communication classes and you can go from this one to this one and then from this one to this one, does not contradict the definition of communication class. But if this is true, then you cannot go from X double prime to X. Because if you can indeed do this, then that would mean that from X you can go to X prime. But then after, from X prime, you can go again to x going through x double prime, that would imply that those three states are in the same like kind of directed cycle, and so they all communicate with each other, and then that would contradict the fact that you have indeed three communication classes. Okay? So assuming that indeed you can go from this class to this class, from this class to this class, but then in this case you cannot exit this class anymore, you cannot leave this one anymore. In this case, you would call those three classes open, open, closed. Okay? So by definition, we said that a communication class is open if starting from this class, you can go outside this class, okay? Which is the case for this class here and the case for this class here. But then here, you see that in this picture, once you are here, you cannot leave this class, and then we would call this communication class closed. All right. So not only we have here the definition of what we mean by a communication class, that's basically an equivalence class for this relationship, okay? And you have extra definition of open communication class or closed communication class. All right, so now that we have all that, let's prove the result. Okay, so to prove the result, at least we need to have in mind the definition of some equivalence relationship. So what is an equivalence relationship? That's a binary relationship that is 1 reflexive, 2 symmetric, 3 transitive. So we need to prove those 3 properties. All right, so reflexivity is easy. Reflexivity means that any element is in relationship to itself. So how can we prove that x communicates with x? Well, you just take in the definition n and m equal to 0, okay? You see that here n and m can be equal to 0, okay? They are in general larger or equal to 0. So if you take both of them equal to 0, you get exactly P0xx is the probability of being in state x given that you are in state x at the same time. That's obviously equal to 1. That's of the form P of A given A. That's equal to 1, which is indeed positive. And so that shows that x communicates with itself. All right, so now how can we prove symmetry? Well, the answer is we don't need to prove anything. That's by definition. If you look at the definition, that's completely symmetric in x and y. You just said that if indeed you can find n and m that satisfy that, by just exchanging the role of n and m and the role of x and y, you get exactly the same thing. So this relationship is indeed symmetric by definition. Okay, transitivity is a little bit more difficult to prove. Transitivity, by definition, means that if x and y communicate, and if y and z communicate, then x and z should communicate. Okay, so you have transitivity of the relationship. So let's prove that. Let's assume that x and y communicate, y and z communicate. Can we prove this? Well, by symmetry that we proved here. The only thing we need to prove transitivity is to prove that if those two statements are true, then we can go from x to z with positive probability. Okay? By symmetry, then we can also go from z to x. So let's only focus on proving that there is a positive probability that we can go from x to z. To do this, I'm going to apply the definition here and say that because x and y communicate, in particular, we can go from x to y in a finite number of steps, let's call it n. So there exists n such that Pnxy is strictly positive, but also because y and z communicate, we can go from y to z in a finite number of steps, let's call it m, that gives you some m such that Pmyz is strictly positive. Now, to prove that from this we can indeed go from x to z in a finite number of steps, we need to find k such that pkxz is strictly positive. Well, the most natural candidate for k, because we know that we can go from x to y in m steps and from y to z in m steps, the most natural choice for k is to take k equals n plus m. And indeed, that's going to work. If you can go from x to y in n steps and y to z in m steps, then you can indeed go from x to z in n plus m steps. And the proof is again based on Chapman-Kolmogorov equations that we just saw. Okay? So the proof is just like that. By Chapman-Kolmogorov equation, you can look at Pn plus m of xz. Okay? Chapman-Kolmogorov equation tells you that you can break this down into n times step transition probabilities and m times step transition probabilities by conditioning on the state at time n. Here I'm going to call this state w. X, y, and z are fixed. They are already used in the slide, so I need another letter. Let's call this state w. And so this is just going to be the sum by Chapman-Kolmogorov equation over w in S of Pn xw times Pm wz. Now, if you look at the terms here, this is a probability, this is a probability. So all those terms are non-negative. They might be equal to 0, but none of them is negative. And at least one of those terms is strictly positive. That's the term for w equals z. If you take, or w equals y, sorry. If you take w equals y here, you get Pn xy, which is strictly positive by assumption, and Pmyz, which is strictly positive by assumption. And so eventually, this sum is a sum of non-negative terms. And so the full sum is larger or equal to one specific term, the one for w equals y, and you get this inequality, but then those two terms are strictly positive. And so that shows that indeed you can go with positive probability from x to z in n plus m time steps. Okay? And so that shows that, again, there is k such that pkxz is strictly positive. And then by symmetry, like I told you, you can also deduce that more generally, not only you go from x to z, but you can also go from z to x. So that shows that x and z communicate. All right, and so that completes the proof of this lemma. We were able to prove reflexivity, symmetry, and transitivity. So we have indeed an equivalence relationship. Now, before we conclude, I want to kind of go back to this notion of transitivity and show you that in fact there was another way to prove transitivity that is more visual but still rigorous and without using any equation. So, and this trick is also going to give you an idea of how to find the communication classes in practice. So, notice that if x and y communicate, y and z communicate, so again that means that you can go from x to z in n times steps, y to z from x to y in n times step, and y to z in m times steps. So if you look at your directed graph associated to your process, those two assumptions means exactly that there is a directed path of length n in, like, from x to y in your directed graph. Okay? And this implies that in your directed graph, you have a path of length m going from y to z. Then clearly, if you have those two paths, if you put them together, that indeed gives you a path of length n plus m, okay, going from x to z and through state y, somewhere in the middle. Okay? So that's another way you can prove transitivity. You can say, in fact, more generally, that if x and y communicate, then this means exactly that there is a directed cycle in your directed graph representation that contains x and y. And this means that there is a directed cycle that contains y and z. If indeed you have a directed cycle that contains x and y and another directed cycle that contains y and z, then that's very easy to deduce from that the existence of a directed cycle that contains x and z. So that's another way to prove the result, more visual, without using any equation. You just say that from the directed graph representation of your process that gives you some visualization of the dynamical structure of your process, you can say that the fact that x and y communicate and y and z communicate implies that there is a directed path from x to y and another directed path from y to z. If you put them together, you indeed get a directed path from x to z. And in general, in practice, to find the communication classes, what you can do is use the fact that x and y communicate, if you look at the definition, if and only if there is a directed path from x to y and another directed path from y to z, which gives you exactly a directed cycle, okay, a directed loop that contains x and y. And so that gives you this. Use the fact that x and y communicate if and only if they belong to the same directed cycle. So once you get a picture of your directed graph, you can keep track of all the cycles, and this is going to tell you that all the states that belong to the same cycle should be in the same communication class. That's how you can easily find the communication classes in practice. All right. And then to conclude this slide, I'm just giving you one last definition. That's the definition of irreducibility. We say that the process is irreducible if it has only one communication class. Okay? So, process is irreducible if all the states in your process communicate with each other. This notion is important. We will see later in this video that irreducibility, in fact, implies uniqueness of the stationary distribution when there is indeed a stationary distribution. So after defining the notion of irreducibility, which is the first main ingredient to study a Markov chain, let's now look at the notion of recurrence and transience, and then later the distinction between null recurrence and positive recurrence, which is the second main ingredient to study a Markov chain. I'm also going to show you how you can use the multi-step transition probabilities to check whether a state is recurrent or transient. And we are going to use this result also to prove another connection between recurrence, transience, and communication classes. And more precisely, we are going to prove that those two notions are class properties. All right, so to define properly the notion of recurrence and transience, the first step is to define what we call the time of kth return in a state. That's defined this way. Y here is a state in S, K is a non-negative integer, and we define Tyk as the first time n strictly larger than the previous return time, so Tyk minus 1, such that xn is equal to 1. So, and of course, to start this sequence, we need to impose some initial condition. We are going to assume that Ty0 is equal to 0. So this tells you that the time of the first return for k equals 1, and I'm just going to write this time Ty after, I'm going to drop the 1. So Ty is going to be defined as the first time n strictly positive, such that xn is equal to y. It's important to assume that n is strictly positive. That's the distinction between the heating time that I defined in chapter 5 and this time of return. To define the time of first return, we need to wait that the process starting at time 0 is going to jump before looking at the next visit in state Y. All right. So in general, the time of the kth return in state Y is defined as the first time after the time of the k-1th return, we are going to visit state Y. So notice that those times might be infinite. Okay, it's possible that for some k finite, tyk is infinite. That means that there will be less than k visits in state Y. In which case, all the tyk for any k after that is also going to be infinite. Notice also that those times are stopping times. Indeed, the event that tyk is equal to n, which is the event that the kth visit in state Y strictly after time 0 is equal to n, only depends on the past of the process. The past including the present. You do not need to know the future of the process after time n to know whether tyk is equal to n or not. So indeed, those times are stopping times for all k and for all y, as I define this notion of stopping time in chapter 5 again. All right. So then, how do we define after recurrence and transience? Well, we need one more definition. That these are kind of probabilities that are attached to those stopping times. We call those probabilities probability of return in state y. For any two states, x and y, I'm going to call rho xy. The probability starting from state x, so this index x means given that x0 is equal to x. So given that we start from state x, what is the probability that ty is finite? That's exactly the probability that starting from state x, the process will ever visit state y. All right, so we define those probabilities, and then from that, we can define the notion of recurrence and transience by looking at the particular case where x is equal to y. And then we have this definition. We say that state x is recurrent if rho xx is equal to 1. So this probability here for y equals x is equal to 1. And transient if at the opposite rho xx is strictly less than 1. Alright, so basically what this means is that x is recurrent if and only if, starting from state x, the probability that we will ever return to state x is finite with probability 1. Okay? At the opposite, state x is transient if, starting from state x, there is a positive probability that we never return to state x. Okay, so that's the definition of recurrence and transience. Now, let's look at a little bit the terminology that we use here. That seems to not match really with the definition. In English, recurrence means something that keeps happening, while transient is something that only happens a finite number of times. So, based on the terminology, in blue here, we want to say that state x is recurrent if, starting from state x, we are going to visit state x infinitely often. At the opposite, state x is transient if, starting from state x, we are going to visit that state only a finite number of times. This is not what the definition says, but from the definition we can indeed prove this result. Okay? From this definition we can deduce that if x is recurrent, then this state is going to be visited infinitely often if we start from it, but only a finite number of times if the state is transient. The way we prove this over definition or over characterization of recurrence and transience is by looking at an extension of the Markov property called the strong Markov property that extends the Markov property that applies to deterministic time, but we need to extend that to stopping time. Okay, so the strong Markov property is exactly the same as the definition in of memoryless, in the definition of a Markov process, but instead of looking at fixed deterministic time, you look at stopping times. Okay, and this stopping time needs to be finite. That you can really think of the strong Markov property as an extension of the Markov property in the same way the optional stopping theorem that we saw in chapter 5 is an extension of the fact that the expected value of a martingale is constant over time. That also applies to stopping time if this stopping time is finite. So I'm not going to prove this result, but we are going to use it. Using this strong Markov property, what we can prove is the fact that the probability that the time of the kth return in state x, given that we start from state x, so the probability that this time is finite, is exactly the same as the probability that this time is finite given that the previous time is finite times the probability that the previous time is finite. Alright, so let me comment a little bit about that. Strictly speaking, we can rewrite this probability by conditioning on a partition. The partition in this case would be this event, the previous time of return is finite, but also the complement of that. But notice that if tx k-1 is infinite, this means that the number of visits in state x is strictly less than k-1, then that would imply that txk cannot be finite. Okay? That's why I can get rid of the second part in the conditioning. That's going to give us basically probability of this event given the complement of this event, which is equal to 0. Alright, so then we can rewrite this as just the product of those two probabilities. And then notice that here, this conditional probability is exactly the probability that given that we already visited state x k-1 time, what is the probability that we are going to visit state x at least once more? Okay, that's this conditional probability. By the Markov property, if this time was fixed, you can say that everything that happened before that time and everything that will happen after that time are independent. Okay? And so you can say that given that we are in some state x at some fixed time, the probability that we visit once more state x should just be rho xx, okay, by memoryless. Now, the strong Markov property tells you that this is again true if you look at a finite stopping time. Now, txk-1 is indeed a stopping time. In the conditioning here, it's finite. And what the strong Markov property tells you is that even if this time is random, it doesn't matter. We know that at this time we have exactly k-1 visits in state x. Then, by the strong Markov property, you can forget everything that happened before that time, before visit number k-1. You can forget all this past of the process, and then restart the process and say that the probability that, starting from this state at this time, we are going to again visit state x, which is the condition to have txk finite. This probability is just the same as the probability that starting from state x at time 0, we are going to ever visit state x. So this conditional probability here, by the strong Markov property, is nothing else than just rho xx. Okay, again by memoryless, by the strong Markov property. And so you can deduce that this probability here is just rho xx, this part is just rho xx, times the same probability as what we had here, but for visit number k-1 instead of visit number k. Alright. Then by using a simple induction, you can again apply the same reasoning here to compute this probability. You would condition on txk minus 1 finite. That would give you a rho xx square and so on, and by induction you can easily prove that this probability is exactly the same as rho xx at the power k. Okay? So conclusion, if you start from state x, the probability that you will visit state x at least k times is exactly the probability that you will visit state at least once at the power k. Alright, so now that we have this equation, we can go back to the definition and see that indeed the definition implies, well, what we expect from the terminology recurrent transient. If state x is recurrent, then rho xx is equal to 1. And then that means that rho xx at the power k is always equal to 1. And so that means that for all k, even very large, the probability starting from x that we are going to visit state x at least k times is always going to be equal to 1. So that shows that the number of visits in state x starting from state x is infinite with probability 1 if you have a recurrent state. At the opposite, if x is transient, then rho xx is strictly less than 1. And in this case, you see that rho xx at the power k is going to converge to 0 exponentially fast as k goes to infinity. And so that shows that the probability that you have infinitely many visits in state x is going to be almost surely finite. I mean, the number of visits, in state x is going to be almost surely finite. So the probability that the number of visits is infinite is equal to 0. All right. So, in fact, we can prove a tiny bit more than looking at the probability for the number of visits. We can just look at the expected number of visits and deduce a slightly stronger result. What we can deduce from that is the fact that state x is recurrent if and only if the expected number of visits in state x starting from state x is infinite. So, it's clear that if x is recurrent, then the number of visits is going to be infinite with probability 1. So this random variable here is infinite, and so clearly the expected value is infinite. The converse is not obvious. It's possible that the number of visits in state x is almost surely finite, but still the expected value is going to be infinite. In the transient case, because this quantity here goes to 0 exponentially fast, that's not what happens. Because this goes to 0 exponentially fast, you can prove that it's not just that the number of visits in state x is almost surely finite. You can prove much stronger result than that. The tail goes to 0 exponentially fast, so the expected number of visits in state x itself is going to be finite, which proves the converse, okay? That proves that transient implies that the expected number of visits in state x is finite, okay? Then, from this result, we can deduce a characterization of the notion of recurrent or transient state looking at the multi-step transition probabilities. And we have eventually the following theorem, which is useful in practice. We are going to use this theorem in the next video when I cover chapter 8 of my stochastic modeling book about random walk. This can be used to check whether the one-dimensional, two-dimensional, three-dimensional random walks are recurrent or transient. So this result says that a state x is recurrent if and only if the infinite sum of the pkxx is equal to infinity. The sum is over all possible integer k. Okay? So this probability here is the probability of going from state x to state x in k units of time. Alright, notice that because we have an if and only if, and because transient means not recurrent, this is the same as saying that state X is transient if and only if this infinite sum is finite. Alright, so how do we prove this result? Well, because we have a characterization of recurrence and transience in terms of expected number of visits in state X, given that we start from state X, to prove this result, it would be enough to prove that this infinite sum is equal to the expected number of visits in state X. And that's indeed the case. You can prove that this is the expected number of visits in state X. The proof is based, again, on an application of the monotone convergence theorem. So the proof is pretty easy. You just notice that this infinite sum here, by definition, if you just look at the definition of the multi-step transition probability, that would be the probability that the process is in state X at time k, given that we start from state X. Okay? Then you can just again argue something that we did many times before, that the probability of an event is the expected value of the indicator function on this event. Okay? So that gives you this expression. Then after, next step, you notice that those random variables that are indicator function, they are non-negative. Okay, so that means that as k increase, so if you look at, instead of looking at the infinite sum, you look again at the partial sum, the sequence of partial sums, at each step you are going to add the expected value of a non-negative random variable, so the sequence of partial sums is monotone. And that's why we can use the monotone convergence theorem. You can think of the infinite sum as the limit of the partial sums, but the sequence of partial sums is a non-decreasing sequence. Okay? So using this, you can apply the monotone convergence theorem here. And what the monotone convergence theorem tells you is that in case of monotonicity that we have here, we can exchange limit and integral. You can think obviously as the infinite sum as a limit of partial sum. You can also think of the expected value as an integral, that's the integral with respect to the probability measure. And so you can exchange infinite sum and expected value. And you get that this quantity here is just the expected value of the infinite sum of those indicator functions on the event that xk is equal to x. Now, if you look carefully at this quantity, this is equal to 0 or 1. Okay? These are random variables that can only take two values, 0 or 1. That's 1 each time the process is in state x. So this is an infinite sum of zeros and ones, and the number of ones in this sum corresponds to the number of visits in state x. So in fact, this infinite sum is nothing else than just the total number of visits in state x. So you can replace this by number of visits in state x, and then eventually we prove that indeed this infinite sum here that we have here in blue is equal to this expected value that we have here. But we just argued before, using this strong Markov property, that x is recurrent if and only if this expected value is infinite. So you get eventually, because that's just the same as this, that this is indeed infinite if and only if x is recurrent, and finite if and only if x is transient. So that gives you this nice characterization of the notion of recurrence and transience. I'm going to show you shortly that you can very easily check if a state is recurrent or transient without looking at this infinite sum in some specific cases. But there are cases where this is a little bit more tricky and you need to look at this infinite sum. Again, this result is useful in practice. We are going to use it in chapter 8 to check whether random walks are recurrent or transient, which strongly depends on the spatial dimension. But it turns out that this result is also useful in theory using this lemma, we can easily prove that recurrence and transients are class properties. So again, I defined that earlier. What we mean by class properties is the fact that all the states in the same communication class must all be recurrent or must all be transient. You cannot have a mixture of different types, recurrent, transient, in the same communication class. In particular, that's going to imply that if you have an irreducible Markov chain with only one communication class, then all the states must be transient or all the states must be recurrent. All right, so how do we prove that transients and recurrence are class properties? That's the next result. They are class properties. Again, that means same across all the same state, all the states in the same communication class. So to prove this result, we are going to use the previous lemma, and in fact, you see that's an equivalence. We are going to use both implications. Okay? So using symmetry, the fact that recurrent means the opposite of transient and so on, to prove this, it's enough to prove that if x is recurrent, and if x and y communicate, then y must be recurrent. Okay? And so, having those assumptions, we can easily prove the result. So again, assume that x is recurrent and that x and y communicate. Because they communicate, the definition implies that we can find n and m, such that we can go from x to y in n time steps and from y to x in m time steps with positive probability. So using the definition of communication, we can fix such n and m. All right. So then, to check that in this case, indeed, y is recurrent, which will also prove that if a state is recurrent, then all the states in the same communication class are recurrent. We need, using this lemma, we need to look at this quantity. So we look at the infinite sum over k of pkxx. If we can prove that this is infinite, okay, by this implication here, we can say that this sum is infinite, so the state is recurrent. All right. And so to evaluate this sum, what I'm going to do is first look instead at the sum for not the pkyy, but pm plus k plus n yy. So why am I doing that? Well, because we know that we can go from y to x in m time steps, and then x to y in n time steps. So the idea is going to be to decompose this probability by saying that instead of going from y to y in that number of steps, we can look at the particular case where we go from y to x in m time steps, then k time steps after we are again in state x, and then after, for the last n time steps, we go back to state y. That's why I'm breaking it down like that using this decomposition. Now, notice that I have an inequality here. Indeed, this sum here is larger than this one. The proof is very easy. In fact, this does not mean that pkyy is larger than pm plus k plus n yy. That's a wrong way to look at this inequality. This inequality is just a basic consequence of the fact that the terms in this sum are the exact same as the term in this sum, except that this sum starts at k equals 0, while the sum here, like the time increment here, starts at m plus n. So this sum here is the same as this sum, except that I removed the first n plus m terms that are all non-negative, and so indeed we have this inequality. Okay, those two sums, like the elements in those two sums are the same, the members are the same, but this one start at 0, this one start later. So this sum is smaller. Now that we have this decomposition here into time, like increment of time, m plus k plus n, now we can argue that to go from y to I in that number of time steps, we can go from y to x, then x to x, then x to y. So using, again, maybe kind of Chapman-Kolmogorov equation, but in fact, we just use something simpler than that. I'm going to just say that the probability of going from y to I in this number of steps, or the event, I should say that we go from y to I in that number of steps, is a more general event than the more specific event that we go from y to x in m time steps, then x to x in k time steps, then x to y in n time steps. Okay? So that gives us this over inequality. Okay? This sum here is larger than Pm yx times Pn xy times again the infinite sum of the pk xx. Alright? So what I did here is just break down this multi-step transition probability into this product, this times that, but then this term and this term do not depend on k, so I can put them outside the sum. Alright, so that's all I did. And again, the inequality comes from the fact the way you have to think about it is really thinking that this represents the probability of an event which is clearly a subset of the event here. This is the probability of another event, but the event here is a subset of the event there. Alright, and so now we are done because we know that Pn xy is strictly positive by our choice of n. We know also that Pm yx is strictly positive by our choice of m. We can indeed choose n and m this way because x and y communicate. So that means that this product here is a product of two strictly positive terms. So the product is again strictly positive. But because x is recurrent, it follows from this lemma that the infinite sum of the pkxx is infinite. So we know that this sum is infinite, and infinity times something strictly positive is again infinite. So that tells you that this infinite sum is indeed infinite. Okay? And then to conclude that y is recurrent, I again use this lemma, but using the converse, using the over implication, to get the fact that this is infinite. I'm using the fact that recurrent implies infinite sum equals infinity. Now, to deduce that y is recurrent, I'm just saying at the opposite, that this infinite sum is infinite, and so by this over implication, y is recurrent. Okay? So again, that shows that if a state is recurrent, then all the states in the same communication class must be recurrent. And then from that, you can also easily deduce that if a state is not recurrent, and so meaning transient, then because we have some if and only if here, you can deduce that all the states in the same communication class are also transient. Okay? It's easy to see, like if something is a communication class, it's very easy to see that the complement of this property should also be a communication, a class property. Sorry. So because recurrence is a class property, then transience, which is the opposite of recurrence, must be also a class property. All right. So we have this, and so this again implies that if you have an irreducible Markov chain, meaning only one communication class, then all the states must be recurrent, or all the states must be transient. That's something important that we are going to use after. And to conclude this slide, I just wanted to give you a trick to check whether a communication class is recurrent or transient. You have basically three cases. Two of them are easy. You do not need to use this lemma in practice to check whether the class is recurrent or transient. But there is a third case which is a little bit more tricky, and to check whether this class is recurrent or transient, you will need to look at this infinite sum. So the first case that is easy, it's the case where your communication class is open. If your communication class is open, again, this means that starting from this class, there is a positive probability that you jump outside the class, you can exit the class. In this case, you can find two states x and y, x in your communication class, y outside, such that the probability of jumping from x to y is strictly positive. This means that starting from state x, there is a positive probability that you exit the class, and we saw that if a class is open, once you exit the class, you cannot return. So that means that starting from this state x, there is a positive probability that you jump outside the class and you will never return to this class. And so in particular, you will never return to state x. This shows that if a communication class is open, then one state at least in this class must be transient, because starting from this state there is a positive probability that you will never go back, which means that rho xx is less than 1, strictly less than 1. Now, because this is also like transience is also a class properly, because you have one transient state in your class, it follows from this lemma that all the other states also are transient. Conclusion, if a communication class is open, then it must be transient. Then, second case that is easy, that's the case where your communication class is closed and finite. In this case, you must have recurrence. So why is that? Well, if you start from this class, okay, the fact that it's closed means that you will stay in this class forever. But because the class is finite, the only way you can stay forever in a finite set is by visiting at least one state infinitely often. Okay? And so that means that this state that you visit infinitely often must be recurrent. Okay? We must have rho xx equals 1, or expected number of visits in this state is infinite. Okay? So closed plus finite implies that there is at least one state in your class that must be recurrent, but because, again, recurrence is a class property, all the other states must also be recurrent. Okay? And so that's how you prove that closed plus finite implies recurrent. In particular, we use this result a lot in practice if you have an irreducible Markov chain, and so meaning only one class, and this class must be closed. If you have only one class, this must be closed. So if you have an irreducible Markov chain with a finite state space, then in this case, you can say for sure that your process is recurrent. Okay, your whole process, all the states are recurrent. There is no calculation. You don't have to do any calculation. That's obvious. You will need to visit one state infinitely often, at least one state infinitely often. And the theory tells you that all the states are in the same communication class because the process is irreducible. And so all the states must be recurrent. All right. The case that is difficult in practice is the case where your communication class is closed but infinite. Okay? So example that appears a lot in practice is when, again, your process is irreducible. You have only one communication class that necessarily is closed, but the state space is infinite. Okay? And in this case, it's not clear whether your process is recurrent or transient. Okay? If you have an irreducible Markov chain, so one communication class, but the state space is infinite, then whether you visit each state infinitely often or you visit each state only a finite number of times is not obvious. And in this case, and only in this case, you need to use this lemma to check whether the process is recurrent and transient. And like I told you, we are going to be in this situation and we are going to use this lemma in the next video about symmetric random walk. We will prove that symmetric random walk can be recurrent or transient depending on the dimension, depending on the spatial dimension of the process. So to be able to answer the first two problems I mentioned at the beginning of this video, namely the fraction of time spent in a state and the mean recurrence time, the last thing we need to answer those questions is the concept of a stationary distribution. So I'm now going to define what we mean by a stationary distribution, and I'm going to show you how we can find all the possible stationary distributions in practice. So the definition of a stationary distribution is here. That's going to be a probability measure pi on the state space S. And in general, we think of pi as a vector in which the number of coordinates is equal to the number of states. And pi x, the x coordinate of pi, is going to describe more or less the probability that the process is in state x. All right? So we said that such a vector or probability measure is stationary for the Markov chain xn if p sub pi of the event xn equals y is equal to pi y. So what I mean here by p sub pi is a conditional probability given that x0 is distributed according to this probability measure pi. So what this means also is that this is the conditional probability given that x0 is equal to x with probability pi x. And so what this equation means is that if for all x, probability that x0 is equal to x with probability pi x, then for all n and y, the probability that xn is equal to y is equal to pi y. And so that means that if at time 0 the probability of being in all the states is indeed distributed according to pi, then that's still true at any later time n. So more or less what this means also is that pi plays more or less the role of a fixed point for the process, but this is a fixed point in the set of probability measure. And so this means that once the process, if the process reaches a stationary distribution pi, then the process keeps evolving. It still jumps, it's not static, but its distribution will not evolve any longer. Okay? So think of pi as some kind of fixed point, but in the set of probability measure. So probably the most useful theorem in practice for about discrete Markov chain is this theorem, which says that a probability measure pi on the state space S is stationary for your Markov chain if and only if pi p equals pi. And here, the capital P I'm using is exactly the transition matrix of your Markov chain. Notice that the number of coordinates of pi is equal to the number of states in S, but also the number of rows and columns of P is equal again to the number of states in S. And so this product is indeed licit from linear algebra point of view. You look at the product of a row vector by a square matrix, and you get in return again a row vector. If pi is solution of this linear system, pi p equals pi, then that's a stationary distribution. So the way you prove the result is by first looking at this quantity, but for a very general probability measure pi, not necessarily a stationary distribution, and see how you can express this quantity using pi and also the transition matrix P. And in fact, what we obtain is the following. the probability given that you start from pi, any possible probability measure on the state space, the probability that you are in state y at time n is exactly equal to the y coordinate of the vector pi times p at the power n. The way you prove that is very easy. You just condition on all the possible initial states. Okay, let's call it x. This is just if you condition on all the possible values of x0, that gives you the sum over x, all the possible x in the state space, of, again, this probability, but given that x0 equals x, times the probability that x0 equals x. Then, like I told you, by definition, this p sub pi is the conditional probability given that x0 is distributed according to pi. And so what this means is that given this conditioning, the probability that x0 equals x is just pi x. Okay, so this probability here is just pi x. Then here you recognize the probability of going from state x to state y in n units of time. That's exactly the n time step transition probability from state x to state y, which gives you this new sum here. Sum over x of pi x times p sub n xy. But we saw just before that the n step transition probability is the same as, the n step transition probability from x to y is equal to the coefficient xy of the matrix P at the power n. And so you can replace this little p sub n here by a capital P at the power n. And this sum just gives you exactly the scalar product of the row vector x with column y of the matrix P at the power n. If you look at this product, again, this scalar product, that gives you exactly the y coordinate of the new vector pi times p at the power n. And so that shows indeed that this here is equal to that. So the way you can read that is to say that given that we start from a distribution pi that might not be a stationary distribution, the probability of being in state y at time n, okay, or I should say in general, the distribution of xn, if we start from the distribution pi, is exactly equal to pi, your initial distribution, times p at the power n. And so multiplying by the nth power of the transition matrix is exactly the same as applying n times step of your Markov chain. Okay? So that's what we have here. Now, using this result, we can easily prove this equivalence here. I'm going to prove two implications. So first, let's assume that pi is stationary. Okay? So this means that we have this equation for all y and n. Then in this case, to prove this equation here, I'm going to start with pi p, look at the y coordinate of that. Okay, then you can apply the previous equation that we just proved, but for n equals 1, and that tells you that pi p y is equal to the probability that x1 is equal to 1, given that you start from the stationary distribution. Okay, but by this equation, by definition of a stationary distribution, if you look at this quantity, but in the particular case where n equals y, that tells you that the probability of this event should just be equal to pi y. And so you get pi y here. And then that's, because that's true for all state y, that indeed tells you that pi p is equal to pi. And so that shows that we have indeed this linear system here. All right, so then to prove the converse, we are again going to use this equation, but for a general n this time. So now let's assume at the opposite that pi p equals pi. Pi is a solution of this linear system. And then I'm going to look at this quantity here, this probability that you recognize here. To prove that pi is indeed stationary in this case, we need just to prove that this is indeed equal to pi y. So for that, again, I'm using the previous equation. We know from this calculation that this quantity is just equal to pi times p at the power n, and we look at the y-coordinate of that, okay? But then I can break down p at the power n into a p times p at the power n minus 1, okay? That gives you this new quantity, but by assumption, pi p is equal to pi. So I can replace the pi p here by just pi, and that tells me that this is also pi times p at the power n minus 1 coordinate y. By using a simple induction, you can keep breaking down this product, and eventually you reach pi times p at the power 0, which is the same as pi, because p at the power 0 is the identity matrix, and then you end up with pi y. Okay? And so that shows that indeed, if pi p equals pi, then for all n and for all y, this probability that is the same as here is equal to pi y. That's exactly the definition of stationary distribution. So pi is indeed stationary. All right. So this is, I would say, the most useful result in practice when you deal with discrete Markov chain. Typically, this system is not very difficult to solve, but there are cases where it's a little bit more tricky, and then I'm going to give you two more tools that you can use in practice to find stationary distributions. So again, this is something that you use in practice, but we can also use this theorem to give some kind of byproduct of this result and other tricks to find stationary distributions. So there are two cases where the algebra is simplified and you don't really need to solve this whole system. That's the case where your process is doubly stochastic and the case where your process is reversible. So what do we mean by doubly stochastic? Well, we say that the process or the transition matrix is doubly stochastic if P transpose also is stochastic. We also need to assume that the state space is finite for this result to work. So what do we mean exactly by that? Well, remember that at the beginning of the video, I mentioned that if you look at the transition matrix P of a Markov chain, by construction, by definition, the sum of the coefficients on each row is equal to 1. Each row adds up to 1, okay? And that's what we call a stochastic matrix, okay? Doubly stochastic means that not only this is true, but also if you look at any column and you look at the sum of the coefficient on any given column, again, the sum is equal to 1. That's what we mean by doubly stochastic. It doesn't matter if you look at a row or a column. Each time you look at the sum of the coefficient, then you get a sum equal to 1. So if you assume this, and you also assume that your state space is finite, then you can easily prove using this theorem that the uniform distribution on the state space, okay? So here we assume that the state space is finite, so that's going to be the probability measure on S such that all the states have the same mass, equal to 1 divided by the total number of states. Okay, so this uniform random variable on the state space must be stationary. So how do we prove that? Well, you just need to check that indeed this uniform random variable is solution of this system. Okay? Now, this is a linear system, so the set of solution of that from the point of view of linear algebra is a vector space. Okay? It's not just, these are not just distribution, that's a vector space that we call basically the set of all the stationary measures as opposed to the set of stationary distribution. So to prove that the uniform is indeed solution of this system, the only thing we need to do is just prove that any vector in which all the coordinates are equal is indeed a solution to this system. And this is easy to prove that the vector with only once is indeed stationary, or at least satisfy this system, it's not a distribution because the sum of the coordinate is not equal to 1, but you can just divide by the number of states, and you will indeed get a new solution of pi p equals pi. So why is it true that the vector with only ones times p is again equal to the vector with only ones? And so that means that this vector is indeed solution here. Well, that's because if you look at this product, clearly what you have is you multiply, let's say we still have it kind of here, column y of your matrix, all the coefficients in column y of the matrix, by all the coordinates of your vector that has only ones. So what you have in return here is for each column the sum of the coefficient on each column, but because the process is doubly stochastic, the sum of those coordinates is again equal to 1. So by definition of doubly stochasticity, or you just need to use the fact that P transpose is stochastic, it's easy to prove that indeed this vector is an eigenvector, okay, for the matrix P. All right, and so this vector is solution of this system, okay? And then that means that if you divide each coordinate by the sum of the coordinate or by the total number of states, then you get indeed a solution to this system again. But now the sum of the coordinate is equal to 1, so that's indeed a stationary distribution. But clearly, the distribution described as this vector in which all the coordinates are equal is by definition the uniform random variable or the uniform distribution on the state space. All right, so that's one case where things are simplified. Another case where things are simplified that we are going to use in the next video when I cover chapter 8 about symmetric random walk. That's the next one is useful when you look at symmetric random walk on some very general graphs, is this one that tells you that if the process is reversible, okay, meaning that it has a reversible distribution, then this distribution must be stationary. So what we mean by reversible distribution is a distribution pi, a probability measure pi, such that pi x pxy is equal to pi y pyx for all pairs of state x and y. Okay? Those equations all together are called the detailed balance equation or detailed balance condition. Okay? So that kind of more or less say that like the probability that you are in state x times the probability that you jump from x to y is equal to the probability that you are in state y times the probability that you go from y to x. Okay? Not all Markov chain have this property, but if you can find a vector pi that is solution to this set of equations, then pi must be stationary. Again, the way you prove that is by using this theorem, okay? We just need to prove that if this is true, then indeed pi p equals pi. And the proof is very easy. You just look at pi p here at coordinate x, then by definition of the product of a vector by a square matrix, it's going to be the sum over y, over all states y, of pi y times capital P yx, coordinate or coefficient yx of the matrix P, but by definition, this is the same as the probability of going from state y to state x. Okay? Now, if you look at this sum here, you have a sum over y, but this term depends on y, these terms depend on y. So the sum a priori is not easy to compute. But because you have those detailed balance conditions or equations here, you know that this quantity here that strongly depends on y is the same as this one that strongly depends on x and not that much on y. So if you do this transformation, then you end up with sum over y again, but this time of pi x pxy. Okay? Because pi x does not depend on y, you can move it outside the sum and only focus on the sum over y of the pxy. But because the matrix, the transition matrix of a Markov chain is a stochastic matrix, which means that the sum over y of the pxy is equal to 1, that's basically the probability of going from x to any of the other possible states that form a partition of omega. The sum of those probabilities should be equal to 1. Those probabilities should add up to 1 as the terms of a probability mass function. And so eventually you get that this sum here is just pi x times the sum of the pxy, which is just equal to 1. And so that's equal to pi x. And so eventually for all x, you get p pi at coordinate x is equal to pi x. That's exactly the condition we have here. And then that's this linear system. And then by this theorem, you can conclude that indeed pi is stationary. So conclusion, any reversible distribution, any vector satisfying those equations is going to be stationary. And it turns out that the reason why this one is useful in practice is because typically in practice, solving, like finding a solution, a particular solution of those equations turns out to be easier than solving this whole system here. So now using this notion of stationary distribution, but also other notion we just saw before of irreducibility, recurrence, and transience, we are ready to answer the first two main questions about discrete time Markov chain related to the fraction of time spent in a state in the long run and also the mean recurrence time. As you will see, those notions are also related to the notion of null recurrence and positive recurrence that distinguish among the set of recurrent states. So first, let's define properly the fraction of time spent in a state. That's this quantity that in the previous slide I called fny. That's the fraction of time spent in state y strictly before time n. This is defined as a new quantity that I'm going to call Vny over n. Vny is the number of visits in state y before time n. Okay, and you divide by time n, that gives you indeed the fraction of time spent in state y before time n. And you just define this number of visits again by looking at a sum of indicator function. That's the sum of the indicator function on the event xk equals y for all k strictly less than n. So you see that this indicator function is either equal to 0 or 1. It's a 1 each time you visit state y. So looking at this sum, indeed, you count the number of visits in state y by time n. If you divide this by n, you get the fraction of time spent in state y by time n. All right, so we want to understand the limit of this quantity. Notice that this is a random variable, but in the limit, this sequence of random variable is going to converge almost surely to a fixed value. And a case that is kind of trivial is the transient case. If you assume that y, state y, is transient, then the number of visits in state y should be finite, okay, by definition of transience, okay? And so that means that this Vny here, this random variable Vny is bounded, okay? Is almost surely finite, even in the limit when n goes to infinity. So if you divide by n and take the limit, then clearly this should go to 0, okay? So that makes sense. If a state y is transient, then the number of visits in this state is almost surely finite. And so the fraction of time spent in this state in the long run, as time goes to infinity, should converge to 0. Okay, so that's one remark we can give here. Y transient implies that the limit of fny is 0. And what we kind of expect is that at the opposite, if state y is recurrent, then state y is visited infinitely often. And so the fraction of time spent in state y must be not 0 in the long run, but strictly positive. However, it turns out that this is not true. We need something slightly stronger than that. The fact that the time it takes to return to state y is almost surely finite is not enough to have a positive limit here. What we need is the fact that the expected value of this time to return to state y must be finite, which is a slightly stronger assumption than saying that the time of the first return is almost surely finite. Okay, so this, like the converse here is not true. Okay, the converse is false. And in fact, to really understand this limit and see whether this limit is 0 or strictly positive, we need those notions of positive recurrence and null recurrence. Okay, so notice that this condition here in both statements, the fact that starting from state y, the time to the first visit, the next visit in state y is finite, is equal to 1. This is exactly the definition of y recurrent that I already gave you before. Okay, so y recurrent means that given that we start from state y, this time ty, the time of the first visit, should be almost surely finite. However, almost surely finite does not imply that the expected value is finite. And that's where we have this distinction between positive recurrence and null recurrence. We say that if better than that, the expected value of this time is finite, then the state y is positive recurrent. But if this expected value is in fact infinite, even if, again, this is almost surely finite, the expected value can be infinite, okay? Then in this case, we say that the state y is null recurrent, okay? So basically, null recurrent is some kind of critical behavior for a state where the state is going to be visited infinitely often, but the expected, so meaning that the amount of time it takes to return to the state is finite, with probability 1, but the expected number of time steps to return to the state is infinite. This is symptomatic of a random variable that is almost surely finite, but for which the tail distribution does not go to 0 fast enough. All right, so now it turns out that I said here that the converse is false, but what we are going to be able to prove is that if state y is transient or null recurrent, then this limit indeed is 0. But if the state is positive recurrent, then this limit is going to be strictly positive. And better than that, the limit is going to be given by the y coordinate of the stationary distribution, and we will prove that, in fact, in the positive recurrent case, we have a unique stationary distribution. So more precisely, I need to define a few more things before. What I mean by the mean recurrence time in the previous slide, which is the expected number of time steps to return to a state, that's this quantity here, expected value of ty, given that we start from state y. This is what I call the mean recurrence time at state y. Okay? And what we are going to prove are the following. We are going to prove first, I mean not first because the order is a little bit weird, but the first main result that we want is the fact that positive recurrence and null recurrence are class properties, exactly like for recurrence and transience. Again, this means that all the states in the same communication class must all be positive recurrent, or all be null recurrent, or all be transient. Okay? Any state is either transient, positive recurrent, null recurrent. You cannot have a mixture of two different types in the same communication class. This is the definition of class property. So that's the first main result. The second main result that is extremely useful in practice says that if your process Xn, your discrete Markov chain, is irreducible, in which case you have only one communication class, and so all the states must be transient, or all null recurrent, or all positive recurrent. In this case, you have two options. Either all the states are transient or null recurrent, in which case we will prove that there is no stationary dissolution. Okay? And the fraction of time spent in any of the states is going to converge to zero, exactly like here in the transient case. Okay? I'm also writing to have a parallel with this other result here, that you can think of this zero as 1 over the mean recurrence time. If the state is null recurrent, or if your process in general is null recurrent, then all the states are such that the mean recurrence time is equal to infinity, and indeed 1 over infinity is equal to 0. Notice that this also works in the transient case. If y is transient, then we have something stronger than that. The fact that basically this time ty is going to be infinite with positive probability, in which case it's clear that we have that the expected value is infinite. Okay? So this is the first part, first possibility. The process is like all the states are transient or all the states are null recurrent. In this case, no stationary dissolution. The mean recurrence time of all states is infinite, and the fraction of time spent in any of the states goes to 0. Notice that this is only possible if your process has an infinite state space. If the state space is finite, then obviously some states are going to be visited infinitely often, and one of the mean recurrence time should be finite. This is only true, this can only be true if the state space is infinite. At the opposite, if you are in none of those two cases, because these are class properties, then all the states must be positive recurrent, in which case we say that the process itself, because it's irreducible and has only one communication class, we say that the process itself is positive recurrent. In this case, we can prove that there is a unique stationary dissolution, okay, and that the fraction of time spent in any of the states is going to converge to the corresponding, almost surely, to the corresponding coordinate of this unique stationary dissolution. Also, the mean recurrence time is just equal to 1 over this limiting fraction of time you spend in that state, okay? So, also you can write that as 1 over the mean recurrence time at state y is equal to pi y, the y coordinate of pi, okay? And we can prove that all those quantities are positive, which shows that indeed all those mean recurrence time are finite, okay? And that follows from the fact that indeed all the states are positive recurrent, and so satisfy that. All right, so the proof of this theorem is a little bit tricky and a little bit long. Before I prove those theorems, I want to explain a little bit how you use this in practice. Because you don't, in practice, use the theorems as they are written. So, in practice, you don't try, when you have a Markov chain, to prove that the process is transient, null recurrent, or positive recurrent by looking at the mean recurrence time. Finding the mean recurrence time directly in practice is very difficult. What you do instead is notice that like basically those two implications are complement of each other, and so you use instead contraposition of those two things. I mean, basically looking at this implication, you have that this is the opposite of that, but here you have no stationary dissolution, here you have one. So combining those two implications, you deduce that the process is positive recurrent if and only if there is a unique stationary dissolution. And that's how you use this theorem in practice. Instead of trying to compute the mean recurrence time, instead you use what I showed you in the previous slide, solving pi p equals pi to try to find a stationary dissolution. If you find one, then that tells you that the process is positive recurrent, and you can deduce the mean recurrence time by this formula. Or if you cannot find any stationary distribution, then that means that the process must be transient or null recurrent. Okay, that's how you use this in practice. You don't really use those implications, even if these are the natural ones. Instead, you use the contraposition of them. If you can find a stationary distribution, then the process is positive recurrent. Then you can find the mean recurrence time by this formula. Or you cannot find any stationary distribution, in which case the process is transient or null recurrent, and you deduce that the mean recurrence time is equal to infinity. Okay, the way we indeed proceed in practice to find a stationary distribution is by again solving pi p equals pi. And basically in this theorem, the uniqueness here follows from irreducibility. And so in fact, hidden in the proof I'm going to give you soon, irreducibility implies that the set of solutions of the system pi p equals pi is a one-dimensional vector space. Okay? That's a linear system, so that you cannot have only one non-zero solution. You have zero is always a solution, but the set of solutions should be a vector space. And so by irreducibility, the set of solutions should be a one-dimensional vector space. You take one particular, like in practice, you take one particular solution of this system, pi p equals pi, and if the sum, so you have two options, either the sum of the coordinate is finite, in which case you can divide your vector by the sum of its coordinates, and then from what we call an invariant or a stationary measure, you end up with a stationary distribution. Okay? And that's going to tell you that indeed the process is positive recurrent. At the opposite, if after solving pi p equals pi, all the solution, all the non-zero solution you find have sum of the coordinate equal to infinity, then that means that you cannot rescale your stationary measure to get a stationary distribution. And then that will mean that the process is either transient or null recurrent. That's how you do it in practice. This trick I just mentioned about the set of solutions by irreducibility of the Markov chain is a one-dimensional vector space, and you just need to look at the sum of the coordinates to determine whether or not the process is positive recurrent or not. This is a trick you use in practice. That's also something I'm going to use in the proof of this theorem. All right, so now enough about how you use that in practice. Now I'm going to focus on the proof of those two theorems. And the proof is a little bit tricky because we cannot prove both theorems separately. The proof of each of those two theorems, those proofs are connected. So the way we are going to proceed is first we are going to prove a stronger version of this second implication here, proving that we indeed have this conclusion without the strictly positive here, but except for that we have indeed this conclusion if we only assume that we have at least one positive recurrent state. Okay? So we have same conclusion but weaker assumption, so that's a stronger implication. Once we have that, we can use irreducibility and the existence of a stationary distribution to prove that all the coordinates of this stationary distribution must be positive. But because they're equal to the reciprocal of the mean recurrence time, from that we will deduce that all the mean recurrence time must be finite. So eventually we will get that starting with at least one positive recurrent state. We have this conclusion, but this part here, due to irreducibility, is going to imply that all those mean recurrence time are finite, and so all the states are positive recurrent. Okay? And so eventually, if you put the pieces together, keeping only the first assumption and the conclusion, you get that one positive recurrent state implies that all the states are positive recurrent. And so this is going to imply this first theorem. So the proof of this theorem follows from the proof of a stronger version of this implication. And then after putting the pieces together, it's going to be easy to conclude that also when we have transients or null recurrence, then we cannot have any stationary distribution. So that's kind of the global idea. The proofs here of those two results are interconnected. So I cannot give you separate proof of the two theorems. We just prove both of them at the same time by proving a bunch of properties. So, so let's prove this implication, which is again a stronger version of the last implication in the previous slide. Let's assume that the process is irreducible. Let's also assume that we have at least one positive recurrent state. Let's call it X. Then in this case, we can prove exactly like in the last conclusion, we can prove that there is a unique stationary distribution pi, and that the fraction of time spent in any state y is going to converge to the y coordinate of this stationary distribution. The convergence is almost surely. Also, the mean recurrence time is equal to the reciprocal of this coordinate of the stationary distribution. Notice that there is only one little thing missing compared to the conclusion that we had before. Here we have that this is strictly positive. Here I'm not going to prove that yet. We need a little bit more for that. All right, so how do we prove this result? This result, there are four natural steps in the proof. First, I'm going to prove that there exists a stationary measure. Okay, and what I mean by a stationary measure, that's basically a vector in which the sum of the coordinates might not be equal to 1. Okay, so that's measure as opposed to a probability. That is also solution of pi p equals pi. But I'm going to call this measure mu sub x. Okay, mu like measure, that's the typical letter we use for a measure, sub x, because the way we are going to build this measure is by using state x, okay, as the starting point, and looking at basically cycles that relies on a trick called the cycle trick, based on the fact that x is positive recurrent. All right, so that's going to be the first step, but notice that if indeed we find a solution to this system, then we can easily find also a stationary distribution this time if you just divide mu x by the total mass of the state space, okay, mu x s, except that it's possible that the total mass is equal to infinity, in which case you cannot rescale this stationary measure to get a stationary distribution. And we will see that indeed we can rescale this measure to get a stationary distribution because x is positive recurrent. The fact that x is positive recurrent will imply that this measure is basically finite measure. The total mass, by that I mean that the total mass of the state space for this measure is finite. So that's the second step of the proof. We are going to deduce from that the existence of a stationary distribution by just dividing by the total mass. To prove this second step, which is much easier than the first one, we only need to prove that this quantity here is strictly positive, but also finite. Okay? All right, so then third step, we prove that this fraction of time spent in state y is indeed going to converge almost surely to 1 over the mean recurrence time at the corresponding state. Okay, that's going to be the next step. The proof of this step 3 is interesting. It relies, among other tools, on an application of the strong law of large number that I proved in chapter 3 in the case where the variance is finite, and again in chapter 5 using martingale theory in the general case where the variance might be infinite. Okay, so step 3 is an application of the strong law of large number, and then finally the last step what is missing here is the fact that this stationary distribution pi is indeed unique, and to prove uniqueness, the only thing we need is to prove this equation here. If we can prove that for any possible stationary distribution pi y must be equal to the reciprocal of the mean recurrence time at the corresponding state, then we have a unique expression for pi. So that shows this equation here, but that shows also uniqueness. All right, so these are the 4 main steps. Then we need a little bit more to prove the theorem I showed you before, but this is the most important part of the proof. So first, how do we prove existence of a stationary measure? Well, that's by using, like I told you, something called the cycle trick. So I show you a picture here of the cycle trick that will help you understand how to prove point number 1 here. It's in fact very natural. If you only look at the equation, that looks like a headache, but in fact if you look at the picture, you see that the trick is very natural. Here, mu x is not a probability measure, that's just a measure, a positive measure, so the total mass does not have to be equal to 1. So to define a measure that would be a good candidate for a stationary measure, so something that is solution of mu p equals mu, I'm just going to start by assuming that state x here, that is the state that is positive recurrent, has a mass equal to 1. Okay? So mu sub x of the singleton x is equal to 1. Okay? I just fix that value arbitrarily. And then, assuming that x has mass equal to 1, how do I decide the mass of overstates? Okay? What is the measure of overstates? Well, you see in the picture here, for instance, I'm taking an overstate y in the state space S, and I'm looking basically at a sample path of the process, and I'm going to look at the number of times I visit state y between 2 consecutive visits in state x. Okay? So if I start in state x, then the time of the next visit in state x is going to be at the time tx by definition, because we assume that x is positive recurrent, then tx is going to be not only almost surely finite, but also finite on average. And then what I'm going to say, looking at this picture, is that, well, if, of course, like the number 3 here, you have 3 visits in state y between 2 consecutive visits in state x, this is a random variable. This thing here, that's what we call a cycle. A cycle is basically the sample path between 2 consecutive visits in state x. But let's assume that this 3 is not really random, that's indeed the expected number of times we are going to visit state y between 2 consecutive visits in state x. Then in this case, we want to say, well, if x has measure 1, and if between 2 consecutive visits in x, we visit y on average 3 times, we want to give measure 3 to the singleton y. And that's exactly the way we are going to construct this measure mu x. Okay? So the way you construct the measure is by starting from state x. You look at, so tx, then t2x, t3x, and so on. These are the consecutive visits in state x. And you look at the expected number of times you visit a state y between those 2 consecutive visits, and you decide that this expected number of visits in state y is going to be exactly the value of mu sub x of the singleton y. All right, so that's defined here. We assume that the mass for the measure mu x of y is the expected number of visits in state y between 2 consecutive visits in state x. So again, the 3 here in the picture is a random variable. That's for this piece of the sample path. here I'm not looking at 3, I'm looking at the expected number, at the expected value of this random variable. So that's indeed deterministic eventually. Number of visits is random, but the expected number of visits is deterministic. And of course, to be able to prove that mu(x) is indeed a stationary measure, so that satisfies this linear system, we need something better than this definition in English. And you realize that indeed you can write this expected number of visits in state y as follows. You can say that this is the infinite sum over n of the probability starting from x that xn equals y and tx is larger than n. How do you prove that? That's not very difficult. You again replace the probability of those two events by the expected value of the indicator function. Now, if you forget about this part and you just look at expected value of the indicator function of xn equals y sum over n, you basically count the number of visits in state y. Okay? If you remove this part, that's the total number of visits in state y. But if you add this part, you basically look at only the visits that happen at time n that are before time tx. Okay? And so indeed, looking at this quantity, again, you replace the probability of this intersection of events by the expected value of the indicator function, you realize that indeed this indicator function of this random variable, okay, or indicator function of this intersection of events, sorry, is indeed equal to 0, 0, 0, 0, and 1 here. And then again 0, and then 1 here. And then 0, and 1 here. And then after that time, that becomes 0 again, because after that time, this condition is not satisfied anymore. Okay, n is going to be larger than tx. So indeed, this infinite sum corresponds to the expected number of visits in state y between two consecutive visits in state x. All right. So that's, again, looking at the picture, that's the most natural candidate. If we assume that mu(x) x is equal to 1, this is the most natural candidate for a stationary measure. So now, how do we prove this? Well, all right, so first I'm reminding you the definition here, mu(xy) is equal to that. This is the mathematical definition. This is more like the interpretation in English. So we want to prove that mu(xp) equals mu(x). I'm going to look at two different cases. I'm going to compare the coordinates of those two vectors, looking first at the states that are different from x. Right? So let's take a state z different from x, and let's look at mu(xp) of z. So what is this quantity? So first, I just write, again, using linear algebra. I'm not using any probability here, it's just linear algebra. By definition, the product of a row vector by a square matrix is just the sum over y of coordinate y of this vector times pyz. Okay? Now, y moves, it can be any of the possible states, but z is fixed. Okay? Again, I remind you that the matrix P here, P is the matrix, the transition matrix, and the coefficient of this transition matrix are those transition probabilities. Alright? So, we just do this. Then, next step, I'm just going to replace mu(xy) by its definition. So, mu(xy) is written here. And so that's exactly what we have here. You recognize this quantity here, this probability is exactly this one. I have, again, the sum over n. And of course, I have the pyz that I had here. But I wrote here that to prove this equation, I use also the monotone convergence theorem. So why is that? Well, because I did not just replace this by this quantity, I also put this infinite sum over n in front of this over sum here. Why can I do that? Well, that's again the same story. Those quantities here and here are probabilities. So if you look at the sequence of partial sums, that gives you a monotone sequence. And here you can basically exchange the two sums. If the state space S is finite, you don't need the monotone convergence theorem that follows by linearity. But if the state space is infinite, then you have to exchange two infinite sums. You can do it using the monotone convergence theorem because the terms in the sum are positive, so the sequence of partial sums is monotone. All right, so we get this expression. So now let's look at this expression more carefully. You have a sum over y, okay, of even that xn equals y, but then after you have the probability of going from y to z, okay? So if you are in state y at time n, and then you jump from y to z, this means that at time n plus 1 you should be in z. And you sum over all y. So in fact you can replace this by just the probability that at time n plus 1 you are in state z. But then because z is different from x, that also implies that tx cannot be equal to n plus 1. Because at time n plus 1 you are not in state x. And so you have to also replace the tx strictly larger than n by a tx strictly larger than n plus 1. And that gives you exactly this expression. Okay? You see I got rid of the sum over y, but then I need to be in state z at time n plus 1, and tx is strictly larger than n plus 1. Then, next step is just to replace n plus 1 by n. Okay? So, those two sums, we want to prove that those two sums are the same. They are indeed equal, except that in the second sum here, I add one probability, the probability that x0 equals z and t0 is larger than 0. So notice that again, I'm using the fact that z is different from x. Because z is different from x, the probability that x0 equals z is equal to 0. So indeed, the only difference between this sum and this one is that in the one at the bottom, I add the term for n equals 0. But that's fine, because the term for n equals 0 gives you a probability equal to 0. So indeed, this sum is equal to this one. And then we are done. We are done because if you look carefully at this quantity, this is exactly the same as here. That's the probability that xn equals z and tx is larger than n. That's exactly this quantity. We just have a z instead of y. And so that means that this quantity, by definition, that's going to be mu xz, okay, which gives you this, okay? And so that shows that indeed mu xp is equal to mu x, at least for all the coordinates that are different from x. All right, so now, next we want to prove that we again have the same equation, but when z equals x, the proof is very similar, not exactly the same. We used a couple of times here that z and x are different, but the beginning of the proof is the same. Here, this first line here is the same as the first line there. I just replace z by x. Here, we did not use that z and x were different. That's only something we use at the next step. But, okay, so now if you look at this quantity carefully, again, you have that at time n, you are in state y. Sum over all y. But then you multiply by the probability of going from y to x. And so that's exactly the probability that at time n plus 1, you are in state x. Okay? You get rid of the sum and you replace this probability here by the probability that xn plus 1 equals x. But then, if tx, the time of the first return in state x, is strictly after n, but also at time n plus 1 you are in state x. That means that now Tx is exactly equal to n plus 1. Okay? Before, because z is different from x, we had Tx strictly larger than n plus 1. Now at the opposite, we have Tx equals n plus 1. Okay? So eventually we end up with something similar, but now we have Tx exactly equal to n plus 1. Now notice also that if Tx equals n plus 1, okay, then that means that in particular at time n plus 1 we are in state x. And so this means that this event implies this event. So this event is a subset of this event. And so the probability of the intersection is just the probability that Tx equals n plus 1. And that's it. Okay? Then you get infinite sum of the probability starting from x that Tx equals n plus 1, sum for n larger or equal to 0, and then clearly, if you look at the sum here, that's just the probability that Tx equals 1 plus the probability that Tx equals 2 plus the probability that Tx equals 3, and so on. These are the sum of the terms of a probability mass function. I remind you that because x is positive recurrent, and in particular it's recurrent Tx, given that we start from x, Tx is almost surely finite. So indeed, this infinite sum should be equal to 1. You have the sum of the terms of a probability mass function of a random variable that is almost surely finite. So this sum is equal to 1. So we get 1. But 1 is also the value of mu x of x. That's how we constructed this measure. I remind you that we said that we fix arbitrarily like the mass of x equals to 1, and we decide the mass of the other states based on that. You can also go back to the definition and realize that the expected number of visits in state x between two consecutive visits in state x, that corresponds to the number of visits in x at each cycle. By definition, the cycles they separate visits in state x. So indeed, the number of visits in state x at each cycle is equal exactly to 1. Okay? So that tells you that mu x is also equal to 1. And so we get that indeed mu x px is equal to mu x. Okay? So we had exactly that for all z different from x, also for z equals x. And so that shows in general that defining this measure, we indeed get a measure such that mu xp is equal to mu x. And so that's a solution to our system pi p equals pi, but the sum of the coordinate is not equal to 1. We only have, at this point, a stationary measure, not a stationary distribution. But we can easily, using the fact that x is positive recurrent, we can easily prove that mu x s is strictly positive but finite, and rescale by this quantity to get our stationary distribution pi. Okay? Like now a probability measure, not just a very general positive measure. So how do we do this? Well, you just say that, okay, the goal is to check that the measure of S for the measure mu x is strictly positive but finite. The fact that it's strictly positive is easy. The measure of S is by sigma additivity of a measure that's equal to the sum of the measure of each element in S, okay, of each state. So all those quantities, of course, are non-negative. So this sum is larger than each of its terms. So in particular, that's larger than mu x. But we just proved that, we just argued that mu x is equal to 1. And 1 is strictly positive. Okay? So that shows that indeed the total mass of S here is at least equal to 1. And so that's positive. Okay, so we do not divide by 0 here. So that's a good news. Now the problem is if the total mass of S is infinite, in which case here you would divide all the coordinates by infinity, and you will end up with a solution that is obvious, that's the zero solution. That does not give you a stationary dissolution. And that's how we deal in practice, okay? In practice, you just solve like mu p equals mu or pi p equals pi. You get a solution, a particular solution. In fact, the set of solutions is a one-dimensional vector space. In the case of irreducibility, that is the one-dimensional vector space generated by this unique solution you found, by this particular solution you found. If the sum of the coordinates, which is here, of your solution, is finite, then you can rescale your solution so that the sum of the coordinates is equal to 1, and you get your stationary dissolution, and you can deduce positive recurrence. But if the sum of the coordinate is equal to infinity, then you cannot rescale your measure to get a dissolution. And then that shows that the process does not have any stationary dissolution. And so it must be transient or null recurrent. Okay, so how do we prove that indeed this is also finite? And that's kind of an interesting aspect of the proof, because that's where we use the fact that X is positive recurrent. Well, it turns out that the total mass of the state space is in fact just equal to the mean recurrence time at state X. And the proof is just here. You just look at the total mass for the measure mu x of S. Again, that's the sum here. And then if you replace by the definition, like the verbal definition, you can say that mu xy is the expected number of visits in state y between two consecutive visits in state x. Okay? That's what I write here. But then, again, you can use the monotone convergence theorem because everything is positive. I already justified all that a lot in this video and the previous videos. You can just put the sum inside. That's an infinite sum, but those are non-negative, and so you have sequence of partial sum is monotone. Expected value is like an integral, so you can exchange infinite sum and expected value. But then the sum, a priori infinite sum, if the state space is infinite, of the number of visits in state y between two visits in x is just the total number of visits in any possible state between two visits in state x. That's what's written here. Eventually, you end up with that the sum over y of this number is just the number of visits in any state between two visits in state x. But that's exactly the total number of visits in any possible state between two consecutive visits in x. That's exactly the number of time steps you need to go from x to x. That's tx, okay? And then you see that indeed the total mass of the state space here by the measure mu x is nothing else than the mean recurrence time at state x, okay? So using the construction we did in 1, you get indeed a stationary measure, but you see how positive recurrence plays an important role. If the process, or if your state x was transient or null recurrent, then this quantity would be infinite, which means that the total mass here is infinite, and then you can prove that each time you try to solve pi p equals pi, you end up with particular solution for which the sum of the coordinate is infinite. That shows that there are stationary measures, but there are no stationary dissolution. And so the process cannot be positive recurrent. But if the sum of the coordinate is finite, which is the case when you have positive recurrence here, then you can rescale your vector here to get a stationary dissolution, and then you deduce that the process is positive recurrent. In this proof, we use it the other way around. We use positive recurrence implies that we have a stationary dissolution, but in practice, we do it the other way around. All right, so we already have, at this point, existence of a stationary dissolution. We don't know what it looks like and anything, But then now we can conclude that this is the reciprocal of the mean recurrence time, and that's also the limit of the fraction of time spent in the corresponding state. So for that, we are going to use two aspects to prove point number 3, that we have indeed convergence of the fraction of time spent in a state almost surely to the reciprocal of the mean recurrence time. So first, you notice that you have this relationship between the number of visits and the times of those visits at state y. Okay, here I'm writing that Vny equals m if and only if Tym is strictly less than n, less or equal to Tym plus 1. That's kind of obvious. You just say that this means that the number of visits in state y strictly before time n is equal to m. That means that the time of the nth visit was strictly before time n, but the time of the next visit should be after that time. And so that indeed gives you that time to the nth visit in state y is strictly before time n, but the next visit is going to be after that time. Okay? So you have this equivalence here, and now an interesting next step where we use the strong law of large number is to say that Tym over n is going to converge almost surely to the mean recurrence time. So why is that? Well, here we use a mixture of the strong law of large number and also implicitly the strong Markov property. So what we are doing here is we look at those cycles, and again, basically what I call a cycle, it's what happens between two consecutive visits in state X. By the strong Markov property, because the visits in state X are stopping times that are almost surely finite, we can use the strong Markov property and say that everything that happened before a visit in state X and everything that happened after that visit in state X must be independent. Okay? And so that shows that consecutive cycles, okay, in the picture I showed you about the cycle trick, consecutive cycles must be independent. But also because the process is time homogeneous, the rules are not going to change over time, then that means that what you see in each cycle should be equal in distribution. Okay? And so from that we can deduce that the times between consecutive visits, okay, are independent identically distributed, like the inter-arrival times. Okay? And so by the strong law of large number, and if you think of Tym, the time of the n visit, as the sum of m times that are independent identically distributed, you can say that Tym over m, okay, so you just rewrite Tym as a sum of m independent identically distributed random variables corresponding to the time increment of each cycle. Then you have a sum of m independent identically distributed random variable. If you divide by m, you get the empirical sum, and we saw that by the strong law of large number, this empirical sum is going to converge almost surely to the common expected value of all those random variables. But that's a sum of random variables that are distributed according to Ty. Okay? And so eventually you have convergence to the expected value of Ty. That's the mean recurrence time in state y. Okay? And so we have this new result, sub-result, and then combining both, you can indeed prove this convergence here. And so you just say that combining 1 and 2, the fraction of time spent in state y should be of the order of, well, m over Tym. That's basically m is kind of your number of visits, plays the role of the number of visits in state y. You divide by TYM, but TYM, you see that's roughly equal to n. So that's number of visits in state y by time n divided by n. That's indeed the fraction of time spent in state y by time n. And because this converges almost surely to the mean recurrence time, then the reciprocal is also going to converge almost surely to the reciprocal of the mean recurrence time. All right. And so that indeed tells you that the fraction of time spent in state y by time n, if you take the limit when n goes to infinity, so fraction of time spent in state y in the long run is equal to 1 over the mean recurrence time. This makes sense. For instance, if you need on average 5 time steps to return to state y, then you kind of expect that the fraction of time you spend in state y should be 1/5. Okay? So this intuitively makes sense, and here you have a rigorous proof. Okay, so now we have all aspects of our theorem, except one thing missing. We still did not prove that pi y is equal to the reciprocal of the mean recurrence time. And of course, if we can prove that for any, like for this stationary distribution, we must have that. This also shows uniqueness of the stationary distribution. So how do we prove that? Then first, I'm going to assume that we start the process from the stationary distribution, and I'm looking at the expected value of the fraction of time spent in state y by time n. If we start from the stationary distribution, then I'm just, step 1, replacing fny by its definition. By definition, it's 1 over n times the indicator function on the event xk equals y. Okay? So I just have that. I'm also using linearity to extract the 1 over n and the sum over k less than n. So we just get this. But again, expected value of an indicator function, that's just the probability of the event. That's what I have here. This step is easy. And then after, here what I'm using is the fact, to conclude, is the fact that if you start from a stationary distribution, from this stationary distribution pi, then the distribution at time k should again be equal to pi. So this probability here that xk equals y is just pi y, and that's it. And so you get 1 over n times sum of the pi y. This does not depend on k. You have exactly n terms in this sum, and so that's exactly n pi y over n, that's equal to pi y, okay? And so we get that the expected value of the fraction of time spent in state y at any time is just pi y. And then from that, we can conclude using the dominated convergence theorem. So what we do here is, again, remember the goal is to prove that this is equal to the reciprocal of the mean recurrence time. So I'm starting from pi y. Then we just prove that pi y is equal to this expected value for all n. So I can take the limit. The reason for taking the limit is that from the previous result here, number 3, we know what is the limit of that, okay? And so I'm looking at the, this is equal to that for all n, so this is equal to the limit when n goes to infinity of this expected value. And then I can put the limit inside the expected value. Again, 2 results allow you to do that, the monotone convergence theorem or the dominated convergence theorem. In this case, if you look at the fraction of time spent in state y, there is absolutely no reason that this quantity is non-decreasing with n. Okay, that's not the number of visits by time n. This one indeed is non-decreasing. That's the fraction of time spent in state y. So this has no reason to be non-decreasing. But clearly, this by definition is a number between 0 and 1. Okay, and because 1 is integrable for a probability measure, we deduce that indeed we can use the dominated convergence theorem. Okay, this is less than 1, which is integrable. And so we can exchange limit and integral, or in this case, limit and expected value. So we get expected value of the limit, but we just proved that the limit of the fny is the reciprocal of the mean recurrence time, so we get expected value of this. Now, you see that ty is a random variable, but the expected value of ty is a fixed number. So eventually here, the reciprocal of the mean recurrence time is not random anymore, okay? ty is random, but not the mean recurrence time. And so eventually you look at expected value of a constant, which is just equal to this constant, okay? And so that shows indeed that pi y here is equal to the reciprocal of the mean recurrence time here. And that completes the proof of this theorem, okay? So that was the main step. The rest is I'm not going to say easier, but that's shorter. Next step now to conclude that, you know, we have irreducibility and positive recurrence implies everything we need, but also the converse and the fact that null recurrence and positive recurrence are class properties. We need this next result. We need to prove that if the process is irreducible and has a stationary distribution pi, then all the states must be positive recurrent. Okay? Combining those two theorems, you will see it's easy to prove that positive recurrence is indeed a class property. So, how do we prove this theorem now? Well, first I'm going to use the fact that because we have a stationary distribution pi, the sum of the coordinates is equal to 1, so pi of x must be strictly positive for at least one state x. That's the same x as the one that was positive recurrent before. Okay, so that's the first step of the proof. Because the sum of the coordinates is equal to 1, then at least one of the coordinates must be strictly positive. Okay, let's assume that this is for x. Now, step 2, I'm going to take another state y, and because the process is irreducible, then x and y must communicate. Okay, so if I take any state y, because they communicate, x and y communicate, in particular, I can find n such that Pn xy is strictly positive. There is also, according to the definition, an m such that Pmyx is strictly positive, but we don't need that. What we want to do now is basically to prove that all the coordinates of this stationary distribution pi must be positive. Okay? To get that this is positive and so this is finite. And so we only need to have this, like Pn xy strictly positive. Kind of the idea is to say, well, pi x is strictly positive, so we spend a positive fraction of time in state x, but because Pn xy is strictly positive also, each time we visit state x, there is a chance that n times step after we visit state y. And so eventually we should spend a positive fraction of time in state y. That's kind of the intuition behind the proof here, but here are the details. You just said that 1 over the reciprocal itself of the mean recurrence time is equal to pi y. That's what we proved here. But then because we assume that pi is stationary, remember this is the same as saying pi p equals pi. So more generally you can say that pi n is equal to pi. Okay? Now intentionally the power I'm taking here, the power n I'm taking here, that's the same n as here. Okay? So that now we can write again, this step is basic linear algebra. I'm not using probability theory. I'm just writing the scalar product of this row vector by column y of the matrix P at the power n. So I get this sum here. We did that several times before. I also remind you that the coefficients of the matrix P raised at the power n are the n-step transition probabilities. That's why I have a little piece of n here. But then you see that all the terms in this sum are non-negative, and one of them is strictly positive. Which one? Well, the one for z equals x, okay? If you take z equals x, you get pi x, but by assumption, we chose x so that pi x is strictly positive, and then the Pn xy is strictly positive by our choice of n. That implies that this is strictly positive, and so that shows that if you have irreducibility and a stationary distribution, then all the terms of the stationary distribution, all the coordinates of the stationary distribution should be positive, okay? And that's a consequence of irreducibility. And because pi y is the reciprocal of the mean recurrence time, that means that this also is strictly positive, so the mean recurrence time must be finite. Okay, so combining those two results, what can we say now? Well, what we can say is that for an irreducible Markov chain, that's the assumption here, if you have one positive recurrent state x, then you have this conclusion. In particular, you have a stationary distribution pi that is unique, okay? But then this conclusion corresponds to the assumption here. So after that, you can again apply that, you still have irreducibility, and you are able to prove existence of a stationary distribution pi, and then applying this second theorem, you get that all the states are positive recurrent, okay? And so eventually, putting both theorems together, you get that if you have irreducibility and one positive recurrent state, then all the states must be positive recurrent. And from that, you can deduce that positive recurrence is indeed a class property. So I only prove that if we have a one positive recurrent state, then they are all positive recurrent if we have an irreducible Markov chain. But that still works if you have, you look only at communication classes. So that shows that we have indeed a class property. The fact that null recurrence also is a class property follows from the fact that if you have two states x and y in the same communication class, you assume that x is recurrent, then y must be recurrent because recurrence is a class property. But because positive recurrence is also a class property, the fact that one is not positive recurrent implies that the other one is not positive recurrent. So that's more a logical trick, like a logic trick, that tells you that one state is recurrent if and only if the other one is recurrent, but one state is not positive recurrent if and only if the other one is not positive recurrent. But being recurrent and not positive recurrent is the same as saying that you are null recurrent. Okay? So that just using this kind of logical thinking that you easily conclude that also null recurrence is a class property. All right. So now we can also conclude this theorem. So how do we do this? Well, the second part, that's what we prove at first. In fact, we prove something stronger. If you assume irreducibility and all state positive recurrent, then in particular one of them is positive recurrent, and we have this whole conclusion that is indeed the same as this one. And then after we also prove that, like here, that should be pi y should be strictly positive. Okay? So, okay, so we have all that, and then we can also from that prove that transience or null recurrence implies no stationary distribution. And that follows from this theorem here. You see that here what we have is if you have irreducibility for an irreducible Markov chain, stationary distribution implies all states are positive recurrent. Okay? And so that means that if you look at the contraposition of that, okay, you just say that the contraposition of that means that for an irreducible Markov chain, okay, if we do not have that, then we do not have that. And so if the process is either transient or null recurrent, so not positive recurrent, then there is no stationary distribution. So that shows also that transient null recurrence implies no stationary distribution. And we also have, like we proved here, that this is going to converge to the reciprocal of the mean recurrence time, but in this case, transient of null or null recurrence, the mean recurrence time is equal to infinity, and so we indeed have that this limit here is equal to 0. So conclusion, either the process is like all the states are transient or null recurrent. Again, null recurrent means that states are visited infinitely often, but the expected number of time steps to return to them is infinite on average. In this case, the fraction of time spent in any state goes to 0, and all the mean recurrence time are infinite. That's by definition of null recurrence are also transient. But the case of interest in practice is when the process is positive recurrent, in which case there is a unique stationary distribution. If you followed carefully the proof, you would see that existence of the stationary distribution follows from positive recurrence, while uniqueness follows from irreducibility. And then in this case, the fraction of time spent in any state is going to converge to the corresponding coordinate of the stationary distribution, which is also equal to the reciprocal of the mean recurrence time. And because all the states are positive recurrent, all those mean recurrence time are finite, and so all those coordinates here are strictly positive. So now let's answer the last main question about discrete-term Markov chain and look at those limiting probabilities. So that's the probability of finding the process in state y at some large time n. So it turns out that contrary to the fraction of time spent in a state that always converges to a limit, at least when the process is irreducible, those limiting probabilities might not converge, and the lack of convergence is due to some periodicity in the process. So now I'm going to define this notion of period of a state, and we are going to prove that the period, exactly like recurrence and transience, is a class properly. Alright, so the notion of period is defined here, the period of state x. So in this notation here, x is a state. I'm going to call dx the period. The period is equal to the GCD, which stands for greatest common divisor of the set of positive integer k, such that pkxx is strictly positive. Because I'm going to use this set a lot after, I'm going to just call it Ix. So have in mind that Ix is the set of integer k, such that you can indeed go from x to x in k time steps. Alright, so the way you find the period in practice is not by using the transition matrix, it's on the contrary by using the directed graph representation. And basically what you do is look at all the directed cycles in your directed graph that contain x. It's enough to look at all the cycles with minimal length, and then you look at all the lengths of those cycles, okay? And then you look at the greatest common divisor of all those numbers. That's going to give you the period. That's how you find the period in practice. Have in mind, and I'm going to give you an example after, that it's possible that you cannot go from x to x in one time step, and still the period of the state is equal to 1. For instance, if you can go from x to x in 2 time steps and in 3 time steps, then the period is going to be the greatest common divisor of 2 and 3, but because 2 and 3 are mutually prime, the GCD is equal to 1. Okay, so the period might be equal to 1, even if you cannot go from x to x in one time step. Alright, so now let's prove that indeed the period is a class properly. So exactly like for recurrence, transience, null recurrence, positive recurrence. So again, what this means is that if two states x and y communicate, then x and y must have the same period. Alright, so the way we are going to prove that is by taking two states x and y that communicate, and so I'm doing the following. I take x and y that communicates, then clearly, by definition, this means that we can find n and m such that we can go from x to y in n time steps and y to x in m time steps with positive probability. So we can fix two integers like that. Also, I'm going to take a k in the set IUI. So if you go back here, you see the definition. This means exactly that pkyy is strictly positive. We can go from y to y in k time steps. And so this condition means that pkyy is strictly positive here. Okay? Then, next step, let's look at those multi-step transition probabilities. Now, the next step is to use those n, m, and k to build numbers, integers, that are indeed in this set Ix. And so for that, I'm going to use those inequalities. Clearly, this is the probability of going from x to x in n plus m time steps. Okay? While here you have the probability of going from x to y and then y to x in n and then m time steps. This is the probability of an event, which is a subset of the event that you go from x to x in n plus m time steps, because you impose the condition that at time n you are in state y. So that explains this inequality here. This probability is indeed larger than this one. But by our choice of n and m, okay, here you see that those two transition probabilities, multi-step transition probabilities, are positive. So the product is strictly positive. Okay? Same story, if you inject a k in between, you can say that going from x to x in n plus k plus m time steps is an event that has a larger probability than the more particular event that you go from x to y and then y to y and then y to x in n steps and then k steps and then m steps. So you have this inequality. Again, like before, those two numbers are strictly positive. This one also is positive. The product is positive. So from that, you can conclude that you can go from x to x in n plus m time steps, or also in n plus k plus m time steps. So that means that n plus m and n plus k plus m, those two integers are both in Ix. Okay? And so I'm going to write that. They are both in Ix. And so by definition of the GCD, dx, okay, by definition of the period of x, because this is the greatest common divisor of all those numbers, in particular, dx is going to divide this number and this number. Okay? So from that, we can deduce that dx divides n plus m and dx divides n plus k plus m. So another way to phrase that is to say that n plus m and n plus k plus m are both multiples of dx. They can both be written as an integer, a positive integer times dx. And so clearly the difference between the two is going to be the difference between two multiples of dx. That's again a multiple of dx. And so you can deduce that dx also should divide only k. Okay, so from that you deduce that dx divides k. So if I recap here, I can say that if x and y communicate, okay, then for any k in IY, the period of x is going to divide k. So that means that the period of x divides all the possible elements in IUI. Okay? So I'm going to use this notation here. The bar here is to say divides. Now I have a dx divides IUI. That's a short I'm using to say that dx, which is a number, divides all the numbers that are in IUI. Or another way to phrase that is to say that all the numbers of this type in IUI are multiples of dx. Okay. And then from that, we can conclude that dx is less than dy. So why is that? Well, that's because if you look at the definition of the period, by definition, dy is the greatest common divisor of all the number in IUI. So that's the largest number that divides all such k. Okay? But dx divides all those numbers also. So dx is just a divisor, a common divisor, while dy, by definition, is the largest divisor. So from that, we have to conclude, yeah, that dx is less or equal to dy. But you see that everything I did here is basically symmetric in x and y, or you could rewrite the same reasoning exchanging the role of x and y, and conclude also that in the same way, dy is less than dx. So basically, by symmetry, you conclude that dx is equal to dy. And so that indeed proves this theorem. The period is indeed a class properly if two states x and y communicate, are in the same communication class, then the period of x is equal to the period of y. All right. So now, let's look at some examples because this notion of period is a little bit tricky the first time you see it. So I'm going to show you some concrete examples so that you see how that works. I'm also going to use those examples to convince you that indeed, if you have an irreducible Markov chain, and because period is a class properly, then that means that all the states have the same period. Then if the period, the common period of all the states is not equal to 1, then those multi-step transition probabilities, P and XY, do not converge. They oscillate, okay? They converge to 0 when the process is transient or null-recurrent, but when the process is positive recurrent, those probabilities are going to oscillate as n increases. So, our examples are here. These are basically the symmetric random walk on the pentagon and on the hexagon. So you have basically a pentagon here, hexagon here. I'm going to describe a discrete term Markov chain with 5 states here and 6 states here. The process is just the symmetric random walk where, let's say you start here and then you jump clockwise, counterclockwise, each with the same probability 1/2. That's called the symmetric random walk on the pentagon, on the hexagon. So, let's apply the result we just saw. Clearly, those two processes are irreducible. From any corner, any vertex, you can go to any of the other vertices in a finite number of steps. So they are both irreducible. They are also both positive recurrent. So why is that? Well, it's just because the state space is finite. So you need to visit a state, like the fraction of time spent in a state must be in at least one state, must be strictly positive. But that's irreducible and positive recurrence is a class properly. So all the states are positive recurrent. Now, using the theorem we proved in the previous slide, we can deduce that because those two processes are irreducible positive recurrent, there is a unique stationary distribution. Okay, there is a unique stationary distribution, and the fraction of time spending in each state converges to the corresponding coordinate. And in this case, things are easy because everything is symmetric, so you can easily guess that the stationary distribution for the symmetric random walk on the pentagon is going to be the uniform distribution that gives mass to, or probability 1/5 to each corner. And for the symmetric random walk on the hexagon, that's going to be the uniform distribution that gives mass 1/6 to each vertex or each corner. Okay? You can in fact prove that rigorously, noticing that the transition matrix of those two processes is doubly stochastic. You can also prove it using reversibility. Okay, so from the theorem we just proved, we can deduce that if you have a random walk starting here, going one way or the other with probability 1/2, then in the long run, the fraction of time spent in each state is exactly 1/5, while the fraction spent in each state here is exactly 1/6. Okay? Now, let's look at the period, and let's see that looking at the period, we have some complication in the case of the hexagon when looking instead at the probability of finding the process in a state in the long run. So, what is the period of the symmetric random walk on the pentagon? Well, you see that when you are in a corner on a vertex, you cannot stay at this vertex. You need at least 2 time steps to come back. Okay? So 2 is in this set here. Okay? You need 2 time steps to come back. But you can also go all around and come back to your initial position in 5 time steps. But 2 and 5 are mutually prime. And so the period in this case is the GCD of 2 and 5, which is equal to 1. So in this case, the period is equal to 1. Okay? So that's the first thing we can say. For the symmetric random walk on the pentagon, the period is equal to 1. In general, you can prove that the symmetric random walk on any polygon with an odd number of sides is going to be the GCD of an odd number and 2. The GCD is equal to 1. But if you look at the symmetric random walk on the hexagon, clearly now the period is 2. Okay? You can go back in 2 steps, or you can redo these 4 steps and so on, or you go all around at 6 steps. So in general, you can prove that the number of time steps you need to return to a state, any of the 6 states, is going to be of the form a multiple of 2 plus a multiple of 6, but a multiple of 6 is in particular a multiple of 2, and so eventually you have that in this case, this set Ix is the set of all the possible even number. The GCD of that set is going to be equal to 2. So for the symmetric random walk on the hexagon, now the period becomes 2. And this is a problem because, well, the fact that the period is 2, and you don't need to look just at this particular case for any possible discrete time Markov chain. If all the states have periods strictly larger than 1, it's clear that the Pn xy, or you can look at the particular case where x equals to y, you can look at the Pn xx, this sequence as a sequence of n is not going to converge. So why is that? Well, that because in this case the period is 2, so that means that Pn xx is always going to be equal to 0, okay, if n is odd by definition of the period. Period equal to 2 means that the number of time steps you need to return must be a multiple of 2. And so Pn xx is always 0 when n is odd. At the opposite, if n is even, the limit, I mean the Pn xx when n is large and even, is going to be equal to 1/3. Okay? And so eventually, you can prove that the fraction of time spent in each state is going to be 1/6. That's what the theory tells us. That's the theorem we just proved in the previous slide. But if instead you look at the probability at some of being in a state at some specific time, if you start from this state, okay, then in the long run at some very large time, you cannot be at this state if the time is odd, but you will be in this state or this state or this state, all three with probability 1/3 if your time is even. Okay? And so for the symmetric random walk on the hexagon, you can conclude that even if the fraction of time spent in each state converges to 1/6, in fact, your P2n plus 1 xx is always equal to 0. While the P2n xx, at least when maybe not n large, but you need n not too small, but like 1 or 2 should be enough, you can prove that P2n xx is going to be equal to 1/3. Okay? So this shows you in this example, but you understand that this is the case for any irreducible Markov chain, like positive recurrent irreducible Markov chain, in which the states have a common period which is strictly larger than 1, then the number of time steps you need to return to your state should be a multiple of a number strictly larger than 1. And so in this case, your n times step limiting probabilities here do not converge, they oscillate. So now the next step is to prove that if at the opposite the process is aperiodic, meaning that all the states have period 1, like in this case, then we indeed have convergence of those limiting probabilities to a limit. So more precisely, if you have an irreducible Markov chain, either all the states are transient or null recurrent, in which case it's easy to prove that the probability of finding the process in a given state, let's say y in the long run, is equal to 0. This part is easy. Now, what we are going to prove is something more difficult, is the fact that in the positive recurrent case, indeed the probability of finding the process in state y in the long run converges again to pi y, but we need to ensure this convergence to have also aperiodicity, meaning that all the states must have period 1. Okay, so more precisely, here is the last main result we are going to prove here. If you have an irreducible positive recurrent aperiodic Markov chain, then Pnxy converges to pi y. So remember that you can compute explicitly Pnxy by looking at coefficient xy of the matrix P, transition matrix at the power n, but I told you that this is only a formula that is interesting in theory, and in practice it can be very difficult to compute. You have to face primes with linear algebra. Now, what this result tells you is that even if we don't really know how to compute the terms of this sequence, we can still find the limit. That's kind of the beauty of the theory of Markov chain. If you combine those three ingredients, then to find this limit, which is kind of the main goal when you study a Markov chain, you do not need to know this sequence exactly. You only need to solve the system pi p equals pi, which is way easier, and then you indeed get the limit. All right. So to prove this theorem, we are going to consider a new process Zn that is again a discrete Markov chain that consists of a pair of processes, so a vector basically, xn, yn, where xn and yn are two independent copies of our Markov chain. Okay, so we assume that those assumptions of irreducibility, positive recurrence, and aperiodicity apply to those two processes. They both have the same transition matrix. Okay, they are exactly the same, but they might start from different states. And the goal is to prove that regardless of the initial state for xn and regardless of the initial state for yn, eventually those two coordinates are going to come together and co-evolve, being distributed according to the same distribution, and that's going to give us this result here. Okay, so that's kind of the idea of the proof, and this one is divided into 3 steps. So the most difficult step is this one, that says that we can find k large, okay? I mean, we can find a capital K large such that for all little k larger than this capital K, pkxx is always going to be positive, okay? We will see soon that this is a consequence of the fact that those two processes, which are basically the same, are aperiodic. That's where we use aperiodicity a lot. Then, using this, we'll be able to deduce irreducibility. So we know already by assumption that xn and yn are irreducible, but what we don't know is that xn also is irreducible. And that's a consequence of this here. Okay, so this step is difficult to prove. Then step 2, that is much easier, is the fact that the process Zn is also positive recurrent. So again, we know that xn and yn are positive recurrent, but we don't know yet that Zn is positive recurrent. In fact, the fact that xn, yn are positive recurrent easily implies that this one is positive recurrent based on the result we proved before. Okay, so this step is easy, and then the most beautiful step of this proof is to look at this time t, that's the stopping time, the time it takes for the process Zn to hit the diagonal. So what I mean by the diagonal is you see that Zn now has a new state space that is equal to S cross S. And what I mean by the diagonal of this state space is the set of x, comma x, such that x is in S. Okay? That's the time at which xn and yn, that's the first time at which xn and yn are going to be equal. Okay? And because Zn is irreducible and positive recurrent, we can prove that this time t is almost surely finite. That's an almost surely finite stopping time. And using the strong Markov property again, we are going to be able to prove that eventually, regardless of the initial state of those two processes, eventually they should have the same distribution after that time t, and that's going to produce our result. Okay, so how do we prove step one? So step one is a little bit tricky and based on some kind of arithmetic and a little bit of like basic number theory. So first, the condition of aperiodicity about xn and yn, these are the same processes, tells us that the GCD of the integer in this set is equal to 1. And so in particular, we can find n and m in this set that are mutually prime. I just remind you the definition of this set. So we can find n and m such that Pnxx is strictly positive, Pmxx is strictly positive, and n and m are mutually prime. All right, so now basic result about prime numbers and like basic number theory is Bézout identity that says that because n and m are mutually prime, we can find two integers a and b such that the linear combination of n and m with those coefficients is equal to 1. So basically, an plus bm is equal to 1. Now, because n and m are strictly positive integer, the only way this can be equal to 1 is if a and b have opposite sign. Okay? So let's assume, for instance, that a is negative and b is positive. Okay, that's the only way you can make that equal to 1, and b must have opposite sign. Then, next step, using this, you can prove that this number c here and this number c plus 1 here, those two numbers are both in Ix. So why is that? Well, that's again a trick that we used before. If you can go from x to x in n time steps, then you can go from x to x in any number of time steps that is a multiple of n. Same for m. Basically, this set Ix, if you think about it, is stable by addition. Okay? That's again a trick we used a lot. If you can go from x to x in n time steps and from x to x in m time steps, then you can go from x to x in n plus m time steps with positive probability. And so that's basically what I'm using here. So more precisely, we know that n and m are both in Ix, and clearly this number, you see I have a minus a times n, but a is negative, so minus a is positive, it's a positive integer, so this is indeed a positive multiple of n. Then also b minus 2a, again b is positive, minus 2a is positive, so this is a positive multiple of m. So this is in Ix, this is in Ix, that's stable by sum, the sum is in Ix. But you can also write c plus 1 as a linear combination with integer coefficient of n and m because we know that an plus bm is equal to 1. Okay, so if you look at c plus 1, you have this expression, but you add that. Then you have minus an plus an, that disappears. And then you have eventually 2b minus 2a times n. Okay? And so c plus 1 can be written that way. Again, 2b minus 2a is a positive integer. And so this number here, times m, is a positive multiple of m. So that's again in ix. So those two numbers, c and c plus 1, are both in ix, meaning that you can go from x to x using those two processes. You can go from x to x in c time steps or c plus 1 time steps. All right, so then next step, we can use this c here to find our k. That's going to work if we take k equals c squared. So let's take k equals c squared and a little k larger than that. And then we look at some Euclidean division. So I'm going to say that because k is larger than c squared, I can write k as c squared plus something else. And I'm going to do a Euclidean division of the remainder here after you remove c squared. And so you can say that there exists q, a quotient, and r, a remainder, that are both non-negative integer, such that, that's the rule in the Euclidean division, such that r is less than c. We look at division by c, so such that, well, k can be written as this c squared plus a quantity, and that's for this quantity that we apply the Euclidean division. This quantity is going to be of the form qc plus r. Right. Then you do a little bit of basic algebra, and you realize that, in fact, this c squared plus qc plus r can be written as c plus q minus r times c plus r times c plus 1. Okay? Now, we just proved that c and c plus 1 are both in ix. So that means that this number k is again in ix, but we need to check first that this number and this number are indeed non-negative integer. Well, clearly that's the case. R, the remainder, is a non-negative integer, and this c plus q minus r, because the remainder is less than c, the c minus r here is strictly positive. If you add q, that's again strictly positive, and so eventually you indeed have that any k which is larger than c squared can be written as a linear combination of c and c plus 1 that are both in ix with coefficients that are positive integer. And so that shows that indeed all k, little k larger than c squared, is going to be in the set ix is such that pkxx is strictly positive. All right. So now, using this, we can deduce that Zn indeed is irreducible. And so the reasoning is here. To prove irreducibility, I just need to take two states in the state space for Zn. Remember that the state space for Zn now is S squared. So I'm taking an x1, y1, x2, y2 all in S, and I want to prove that we can go from x1, y1 to x2, y2 with positive probability for the process Zn, and we can do that in a finite number of steps. So using the fact that not Zn is irreducible, because that's what we want to prove, but using the fact that xn, yn are irreducible, we can find n such that we can go from x1 to x2 in n time steps. And we can find m such that we can go from y1 to y2 in n time steps, which makes this product here strictly positive. Okay? So we fix n and m such that we have this. Then, using this nm and the fact that for k large enough, the pkxx is strictly positive, that also applies to other states. you would have to choose another nm and so on, but you take the maximum of some kind of C1 square and C2 square, where the C1 and C2 depend on X and Y, okay? In this case, I don't call them X and Y, but for those states, eventually, you can say that the probability starting from X1, Y1, that at time n plus m plus k, you are in state X2, Y2, okay? Is exactly equal to the probability that we go from X1 to X2 in that number of steps, n plus m plus k, for the process Xn, times the probability that we go from Y1 to Y2 in the same number of steps for the process Yn. Here, that's the same multi-step transition probabilities that are shared by both processes because they are copies of the same Markov chain, okay? So here we have indeed that this conditional probability is equal to that, and here implicitly what I'm using is the fact that these are independent copies because they evolve independently. The probability of going from this state to this state for the process Zn is exactly the probability of going from this state to this state, and times the probability of going from this state to this state for each of the two processes. I can multiply the probabilities by independence. And then after, again, usual trick, you can break down this first probability, saying that the probability of going from x1 to x2 in n plus m plus k time steps is larger than the probability of going from x1 to x1 in m plus k time steps times the probability of going from x1 to x2 in n time steps. Okay? Same trick that we used a lot in this video. I do the same for the probability of going from y1 to y2, except that now instead of extracting n, I extract m. I'm doing that intentionally so that here we have a Pn x1, x2, which here, by assumption, is strictly positive, and the Pn y1, y2 here is also strictly positive. So this and that are positive, okay? Then for the other ones, we don't really know, but we have this k here that can be increased, and we know from the previous result here that we have pk xx or pk of a state, comma, the same state, strictly positive for k large enough. And then to conclude, I'm just taking k large enough but finite, so that this is strictly positive and this is strictly positive. So that tells me that for k large enough, this conditional probability is strictly positive. And so that shows that indeed, from any state in S square, the process Zn can go to any other state in S square in a finite number of steps with positive probability. Okay, so we conclude that the process Zn is indeed irreducible. That was the difficult part of the proof. Next part, how do we prove that the process Zn is also positive recurrent? This might be extremely difficult. In fact, that's easy. Using the result we proved before, we saw that if a discrete time Markov chain, and Zn is a discrete time Markov chain, is irreducible, then it's going to be positive recurrent if and only if it has a unique stationary distribution. So to prove positive recurrence, it's enough to find a stationary distribution for Zn. But there is one that is obvious. That's what we call the product measure that I define as pi hat xy. Again, x and y are two states in S. And so xy is in S square. Okay, so that's a typical state for the process Zn. And I just assume that the probability under this distribution pi hat, the probability of xy is just pi x times pi y, where pi is the common unique stationary distribution of xn and yn. And it's extremely easy to prove that indeed this new probability that we call the product measure, okay, of pi by itself is stationary for Zn. Again, that follows from the fact that Xn and Yn are both independent, okay? So we get eventually that, combining step 1 and 2, that the process Zn itself, okay, we knew that Xn, Yn were irreducible positive recurrent, but if on top of that you add a periodicity for those two processes, then you can deduce that the process Zn also is irreducible and positive recurrent. And so that means in particular that according to the theory we saw and so on, that eventually, starting from any possible state, we are going to eventually reach the diagonal in a finite time. I'm going to call this time t. So from irreducibility and positive recurrence, we can deduce that time t is almost surely finite. Yeah, I forgot to say that this existence of stationary distribution implies positive recurrence. And so we have indeed this result. Now combining the two, like I was saying, we can deduce that this time t, this stopping time t, is almost surely finite. And so in particular, you can, by combining step 1 and step 2, say that the probability that t is larger than n should go to 0 when n goes to infinity. Okay, so here I have a picture of what's going on. Let's assume that you have S here, you have S here again. So the state space of Zn is going to be this square, S cross S. And then think of this Z0 as, meaning that X0 is here and Y0 is here. Okay? Same X1 is here, Y1 is here, and so on. Okay. So then time t is defined as the first time at which we hit the diagonal. So maybe we jump here, 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 and then here we jump there. And time 1, 2, 3, 4 is going to be the time at which we hit the diagonal. So again, I remind you, I define the diagonal as the set of x, x, such that x is in the state space S. All right. So again, because the process is irreducible from any state, you can go to any other state in a finite number of steps with positive probability, because we also assume positive recurrence. Okay, we obtain that indeed we can go from any state to the diagonal. Okay, and this in a time that is finite on average. And so clearly we have this result here. Okay, that's a direct consequence of irreducibility and positive recurrence. One way to think about it is using the previous result, saying that the combination of the two implies that the fraction of time spent in state x, y is going to be exactly pi x times pi y, but we prove that they both should be strictly positive. So you spend a positive fraction of time in each state in S cross S, and so you spend a positive fraction of time on the diagonal. And then that means that eventually you need to reach the diagonal. You are going to reach the diagonal in a finite time. All right, so now to conclude, we are going to use the fact that because those two processes are independent and may start from different initial states, they are not equal in distribution at first. But after time t, and we know that t is a stopping time that is almost surely finite, after that time, or at that time, those two processes, xn and yn, are equal. Okay? And by the Markov property, you can kind of forget, by the strong Markov property that we can apply because t is an almost surely finite stopping time, you can say that everything that happened before time t does not matter to predict the future. And because of that, you can say that, well, because xn and yn are equal at time t, and because they are copies of the same Markov chain with the same transition matrix, then after they are going to again evolve independently, but being distributed according to the same distribution. Okay, so that's kind of the key to conclude. I'm going to use that. Notice that after time t, and so meaning for n larger than t, xn is equal to yn in distribution. Again, consequence of the strong Markov property that we can apply because t is an almost surely finite time. And so because they are equal at time t, once they are equal, they are going to co-evolve independently but according to the same distribution. Okay. So using this, we can show the following. This other property is the same using basic symmetry between xn and yn. We can decompose the event that xn is equal to y by injecting some t less than n and t larger than n, okay? Those two events form a partition of omega, so indeed this probability is equal to the sum of those two probabilities. Then, next step, here I'm using the fact that if t is less than n, that means that at time n is after the time those two processes met, and we know that after that time they are equal in distribution. Okay? So I can just replace the probability that yn is equal to, probability that xn is equal to y by probability that yn is equal to y. Those two events have the same probability, not at first, but they have the same probability after time t, and we are on the event that n is larger than t, so we are indeed after time t. Okay, so that's what I'm using here. This probability is equal to this one because of this property here. Then after here, I'm just getting rid of the xn equals y. Probability of an intersection is less than the probability of only one event. I just keep the t larger than n. I want to keep this one. This goes to 0. Okay? And then I can again do this at the next step and say that here I have the probability of an intersection. I can just get rid of the part where t is less than n. Okay? I have, of course, an event here which is larger than this event. So this probability is indeed less than this one. Okay? So eventually we get that the probability that xn equals y is less than the probability that yn equals y plus the probability that t is larger than n. By symmetry, we have the same inequality exchanging the role of x and y. And then those two things imply that the absolute value of this probability minus this probability, okay, should be less than this probability, but that probability goes to 0. And so that shows that eventually this probability and this one should converge to the same value. Okay? So that's the next step here. We have that for all state y, if you have two independent copies of the same Markov chain that is irreducible, positive recurrent, and aperiodic, then no matter the initial state for xn and yn, eventually, when n is large enough, eventually the probability that xn is in state y is close to the probability that yn is in state y. Okay? It seems that this should imply the result that says that the limiting behavior does not depend on the initial state, and so it seems that the limiting behavior should be described by pi. The way you conclude properly is by choosing some specific values for x0 and y0 so that we exactly get those two quantities. So how can we get the Pn xy? Well, that's simply by assuming that x0 is equal to x. Okay, if you assume that x0 is equal to x, then this is exactly the probability of going from state x to state y in n time steps. That's Pn xy. Okay? And then to get the pi y here, you just assume that y0 starts from the stationary distribution pi. Okay? And by definition of the stationary distribution, it's like a fixed point in the set of probability distribution. This tells you that for all n, the probability that yn is equal to y is always equal to pi y. And then we are done. You just conclude like this. If you take x0 equals x and y0 not equal to a specific state but distributed according to pi, meaning that y0 equals x with probability pi x, then in this case you see that this quantity is exactly equal to this one, this quantity is exactly equal to this one, and you know that this goes to 0, okay? And so eventually you have that the difference between Pn xy and pi y goes to 0, and so that indeed shows that this limiting probability, thanks to the fact that we have aperiodicity that implies irreducibility of the n, implies indeed that Pn xy is going to converge to pi y. That's all for today. Thank you for watching. In the next video, I'm going to cover chapter 8 of my stochastic modeling book. That's the chapter about random walks, and I'm also going to tell you about their connection with electrical networks in physics.